Hi, so today I start with the next important topic in the series of 50 most important topics of mechanical engineering for GATE. I have already uploaded you some topics, and today I am going to take a topic of fluid mechanics. This topic is something which is very important for mechanical and civil engineers, and in this topic I am going to discuss with you dynamics part of the fluid mechanics. That includes the kind of forces we have in fluids. Solids and fluids are different as far as the kind of forces are concerned. In fluid we talk about certain different kinds of forces: gravity force, pressure force, viscous force. That is what I am going to discuss with you. And after that I am going to discuss with you Euler equation, which is the equation of motion, and integrating that we will get a Bernoulli equation. We are going to discuss how Bernoulli equation can be used for ideal fluids, real fluids, how Bernoulli equation is to be used to calculate the direction of flow, and how Bernoulli equation is to be used for pumps, turbines. If there is a pump or turbine, how we have to find out Bernoulli equation at two sections, which includes pump also. And then I am going to discuss with you certain devices which are based on Bernoulli equation, like Orifice meter, Venturimeter and pitot tube. In my opinion, fluid mechanics mein this dynamics is the part which is a very small part. We are going to complete this in 1 to 2 hours of video along with questions, and this has a very high probability of questions from fluid mechanics. There are other topics which are very vast and probability of questions is little less, but this topic is a concise topic and a very important topic for written exam also, interview also. That is what I am going to discuss here with you in fluid dynamics. Now first of all, I start with the term dynamics. You know, fluid mechanics is consist of three parts that already I have discussed. I'll just again start from here. Fluid mechanics word means something which can move, or which is moving or not moving is separate, but which can move. Analysis of that is called mechanics. Fluid, we already know gas and liquid is called fluid. So fluid mechanics means mechanics of fluids. Mechanics has three parts. One is called statics, another is called kinematics, and third is called dynamics. So that also in the beginning lecture I have already discussed with you the meaning of these three. Statics means when the fluid is at rest. That means the fluid is not flowing, it is not flowing, it is at rest. Something like a fluid in the reservoir or dam, that is a part of statics. In this statics we study hydrostatic law. That is a very, very important topic. Hydrostatic law and Pascal's law. Hydrostatic law, Pascal's law, floating body, sink bodies, all these things are basically part of the fluid statics. That is something which we have already discussed. Now, what is kinematics and dynamics? These two things are studied when fluid is flowing. So when the fluid is flowing, that comes under the kinematics part or dynamics part. Now, when fluid is flowing, answer is why it is flowing and how it is flowing. These are the two things we can answer. Why the fluid is flowing and why part is taken care of dynamics. That means it is the cause why the fluid is flowing, and how it is flowing, that is the kinematics part. Kinematics means effect part, why it is flowing, what is the reason for its flow, and how it is flowing. Now in the typical why and how, in the typical kinematics and dynamics, what we are going to study is this. In the dynamics part we are going to study force, power, energy, torque, etc. These are the cause, these are the why part fluid is flowing. Let me ask you a question. Why the fluid flows in the river or canal? You will say, sir, that is because of the gravitational potential, that is because of the datum difference, high gravitational potential, low gravitational potential, and the fluid is flowing. That means there is a gravitational force. Why there is a wind blow? You will say, sir, because of the pressure difference. So that means there is some kind of force, gravity force, pressure force, some kind of force which is making fluid flow. So that why part is taken care of in the dynamics, that is the cause of fluid flow. And when we talk about kinematics, that is, how do we study kinematics? We study velocity, acceleration, we study the momentum, we study the discharge. Now if the fluid is flowing, let us say the fluid is flowing in a pipe, I am going to ask you, if the fluid is flowing in the pipe, what is the discharge of that? what is the velocity of that? If the fluid is flowing in the river, what is the discharge of that? What is the velocity of that? That means what is the effect part, or how the fluid is flowing, that part is taken care of in the kinematics. Now if you see all these three, kinematics, statics, dynamics, they are the three chapters of the fluid mechanics. So mechanics, statics, kinematics, dynamics, that is the part he is going to ask you. Now let me tell you, sometime he asks you in the interview that out of kinematics and dynamics, which one is input and which one is output. So as I told you, dynamics is input and it gives to kinematics part. That means if there is a force, it leads to change in momentum, or you can say it leads to acceleration, velocity of flow, etc. So we normally say that dynamics becomes the input or cause and kinematics becomes effect. But let me tell you one thing, sometimes kinematics is input and dynamics is output. Suppose there is a fluid which is flowing. Now think of a jet. The fluid is flowing through a jet, and that fluid jet hits some kind of blade, and that jet is basically applying the force on the blade. So in this case, the change in momentum of the jet becomes input and the force which it applies becomes the output. So it is not that always dynamics is the input and kinematics is the output. Sometimes kinematics is the input and dynamics becomes output. Typically in the hydraulic turbines, there is a fluid which comes, and that fluid has energy in it, that fluid has velocity in it, and when you change the direction of flow, then there is a change in momentum, and that change in momentum eventually is giving you the force. So kinematics becomes input and dynamics becomes output. So remember, this question can be asked in the interview, kinematics and dynamics part. Now from where this kinematics dynamics part correlation comes, or what is the relation between kinematics and dynamics part? There is a Newton's second law which all of you have done, second law of Newton. What it says is this, second law of Newton says external force is equal to dp over dt, and what is p? This is the linear momentum. How do you write linear momentum? Is ddt of mass into velocity. So we will say external force acting on a body is equal to rate of change of its linear momentum. Now let me tell you how this second law is written differently for solids and liquids. For solids, we say that F is equal to dmv over dt, and we know mass of the solids is constant, so it is taken outside, and this formula becomes F is equal to ma. That is the formula which we get for solids. He is going to ask you in the interview, how do you write the second law of Newton for liquids and fluids and solids. So for solids, you will say, sir, mass is constant, it is taken out, and I can write this formula as F is equal to ma. Now when we go to fluids, now you know in the case of fluids, the trouble is fluids actually flow. So it is not the question of mass. In case of fluids, there is a normally question of mass flow rate. So we do not talk about mass, we talk about mass flow rate, or we talk about m dot and not m. Let us now see how it is going to be opened for fluids or for liquids and gases. Let us say it is mv. Now mathematics is going to tell me that it is equal to m dv over dt plus v into dm over dt. That means first factor differentiation of second differentiation of the first. This is how you open up if mass and velocity both are assumed to be changed with respect to time. This is how we can open it. Now let us say we assume the uniform flow rate. Uniform flow rate means that velocity is not changing as the fluid is flowing. And where do you observe this? If I give you any uniform cross section pipe where area is not changing, continuity equation is going to tell you that if area is not changing, then a1 v1 is equal to a2 v2, and hence the velocity is not changing. If the velocity is not changing, this term is going to be 0, and I am going to get this as v into dm over dt. Now what is dm over dt? I can write it as v into m dot, mass flow rate, and later on I am going to discuss with you that mass flow rate can be written in terms of discharge as rho into q into v. So what is rho? Rho is the density. What is q? It is a discharge in meter cube per second. So if I multiply density, which is kilogram per meter cube, with meter cube per second, I am going to get kilogram per second as the mass flow rate. So this F will be equal to rho qv. This what I have answered is, if he asks you in the question or in the interview that kinematics and dynamics, which equation can you tell us which connects the kinematics part with the dynamics part? You will say, sir, Newton's second law. This part is the dynamics part. Why it is the dynamics part? Just now I told you it is the forces or that particular cause which makes the fluid flow, and this one is the kinematics part. Kinematics part because it tells you about the velocity, acceleration, momentum change, so that is the kinematics part. Now this equation links kinematics and dynamics, and then he is going to ask you how do you write the second law of Newton for solids and fluids. This is what we have written for solids and fluids, and later on I am going to discuss with you that this particular right hand side, this actually is called inertia effect. So this entire thing is called inertia effect. That means there is a force which is external force, that can be any force, and that force is going to change the inertia of the body. You must have studied the first law of Newton also, that when the body is in the state of rest or in the state of motion would like to be in that state unless until it is acted upon by some external force. So suppose I apply some external force, it is going to change the inertia of the body, and inertia of the body can be measured in case of the fluids something like this, and for solids mass is the basically inertia of the body. So right hand side whatever we are getting Newton's law of motion, that actually is the inertia part of that particular fluid or body. This is what we need to remember. Now let me come back to our main topic, that is the dynamics part, whatever we are doing for the fluids. Now in this main topic of dynamics, let me tell you, in case of solids and fluids there is a small difference. As far as the solids are concerned, we do not differentiate the type of forces. We do not say that this force is there's a gravity force, a pressure force, this force is acting, that force is acting. But in case of fluids, we categorize the forces, and in the fluids we get some particular important or significant fluid forces. Let me write those names. First, most important is the gravity force. Gravity force. Now, you know, whenever fluid flows in the river or canal, it is because of the gravity or potential gradient. The fluid keeps on flowing there. That is called gravity force. Next significant force is called pressure force. This is called pressure force. So there is a gravity force, there is a pressure force. Then third comes is viscous force. Viscous force. Next, let me name is turbulent force. Turbulent force. Next is compressibility force. Compressibility force. So you need to remember some name of the forces: gravity force, pressure force, viscous force, turbulent force, and compressibility force. Now in case of fluid flow, you will come across some particular significant force in certain situation. Like as I told you, open channel flow or fluids flowing in the river or your canal flow, these all are gravity forces. These are significant forces which are gravity forces. Similarly, in case of pipes, the force which is significant is the pressure force. Viscous force is when viscosity is more, then effect of viscous force, normally it is a resistance force or friction force, is more significant. Then turbulent force, when the effect of I will say effect of viscosity decreases, then effect of turbulence or mixing increases, and in that situation turbulence effect is more. You must have observed cavitation phenomena when fluid is flowing at high velocity and it goes through narrow section, then pressure decreases to a great extent and fluid starts boiling and cavitation phenomena occurs. So that is all turbulent effect actually. So compressibility force, when the fluid is flowing at a very high speed, then compressive behavior. Gases are compressible, liquids also start behaving in a compressible way if obviously that particular velocity of flow is very high Mach number pe that effect can be observed. So we get different kind of forces in the fluids. Just remember the name. What is more important is this, that when we consider these two forces, then that analysis is called Euler's analysis. So Euler's equation of motion consider gravity force and pressure force. That is something which you have to remember. If I add one more force into this, gravity, pressure plus if I viscous force, then that equation is called Navier-Stokes equation. So always remember that Navier-Stokes equation is connected with viscous effect. So think of viscous force, think of Navier-Stokes equation. And let me tell you, in GATE exam or BTech, you do not study the viscous or Navier-Stokes equation. You study more Bernoulli equation and Euler equation, because Bernoulli equation is the equation of energy equation or energy conservation equation for ideal fluid. We assume that the fluid is not having viscosity, but that is a wrong assumption, because every fluid has some kind of viscosity. So in BTech level, you study more about Euler equation and its integration, that is Bernoulli equation, and Bernoulli equation assume that there is no viscosity, but in actuality the fluids are viscous, and hence we need to analyze the real fluid, which is done through Navier-Stokes equation. So after GATE exam, if you go to masters or if you go to interview for masters, remember that Navier-Stokes equation he will ask you in the interview or written exam, so prepare it well for that. Now if I add one more force, then turbulent force, if I also add, this analysis becomes Reynolds analysis, and Reynolds equation is used to analyze this. So think of Reynolds and think of turbulence. So think of these words which are important words: Euler, gravity force, pressure force, Navier-Stokes equation, viscous force, and Reynolds equation is turbulent force plus all this. Navier-Stokes, viscous, Reynolds, turbulent, and these forces are always there. So these all forces collectively are basically part of external force which is acting on the fluid. Now again let me repeat what we have started with, from where we have started. We said that Newton's second law says external force is equal to rate of change of momentum. In case of fluid, what is external force? We will say external force can be sum total of gravity force, pressure force, viscous force, turbulent force, compressibility force. Now let us say in certain situation turbulent force is not there. You are not going to consider that. Now if I only consider two forces, I can only consider two forces. If I only take one force, I can only take one force. So this side, which is the dynamics part of the fluid flow, that basically consists of certain type of forces. Remember the name of the forces, that becomes the dynamics. And what is this then? This one is the inertia, or this one is the kinematics part of the fluid flow. This is how we analyze the dynamics. So I hope now concept of dynamics, what is the meaning of dynamics, how it is related to kinematics, what are the various forces in the fluid, and what are the various equations related to these forces, that concept is clear to us. Now I come to our important equation of motion, that is called Euler's equation of motion. Remember that Euler is equation of motion, whereas Bernoulli is equation of energy. Equation of motion, equation of energy. Now what is Euler's equation of motion? Let me give you the equation. I am not going to give you derivation for that, that is not required. dp by rho plus g dz plus v dv is equal to 0. That is the equation of motion. Whenever we want to write this equation of motion, it is to be written on particular flow line or streamline. So if there is a streamline and it is having some kind of curve, you need to calculate the pressure, velocity, datum terms on that particular streamline. He is going to ask you that Euler equation or Bernoulli equation, whenever you calculate the terms pressure, datum, velocity, where do you write them? At section 1 and section 2. You will say, sir, on the streamline or flow line. Now what is this dp? This dp is called pressure gradient. This is called pressure gradient. How is this written? It is written as, sir, P2 minus P1 by rho, or P2 minus P1 if I am writing dp, final minus initial. What is dz called? It is called datum gradient. This is called potential gradient or datum gradient. You can call it potential gradient also. And what is dv? dv is called this velocity gradient. It is called velocity gradient. Gradient means difference, change, and over the length or something, that is the part of it. So this all three terms are made up of, which are called Euler equation. These terms made up of Euler equation, and this is the equation of motion. You need to remember these three terms. Let me ask you a question. What kind of forces do you see in this equation? You will say, sir, pressure force and gravitational force. But what is this then? What is the third thing? Answer is, sir, this is the inertia part of these forces. This is the effect part of these forces. That means if I write this equation like this, dp by rho plus g dz is equal to minus v dv, this particular part becomes external force of Newton's second law, and this particular part becomes the dp by dt, whatever we have written. So we will say that, sir, in Euler's equation these are the two forces and right hand side is the effect of that. And why negative sign? Because whenever pressure decreases, velocity increases. Whenever the datum decreases, velocity increases. As you know that if I throw this pen from high datum, z is decreasing but velocity is increasing. Z is decreasing means z2 minus z1 is negative. dv increasing means v2 minus v1 is positive, and hence this negative sign has come. So if we ask you in the Euler equation what are the three forces you see, you say, sir, only two forces. Third is the effect of that, which is called inertia force, and it can be written as this for second law of Newton. Now let's go for what are the assumptions of Euler equation. So let me give you the assumptions of Euler equation now. What are the various assumptions of Euler equation? And let me tell you, the assumptions of Euler equation and assumption of Bernoulli equation are same, but you need to rote memorize them because written exam may also they come, and also these are the part of your interview also. So what are the assumption is? First assumption is flow is a steady. That is the first assumption for us. What do you understand by steady flow? Steady flow means there is no change with respect to time. So if there is no change in particular parameter with respect to time, that is called a steady flow. Like suppose velocity is constant with respect to time. So when we consider the variation with respect to time, we are not to change the space. We are to assume the constant space or constant position. That means velocity of flow at particular section with passage of time is not going to change. Anything which is not changing with respect to time or curly of any particular parameter, let's say velocity is not changing with respect to time, that is called steady flow. That is the first assumption for us. Second assumption is non-viscous. Non-viscous, there is another term for that, it is called inviscid, and there is another term for that, it is called ideal flow. That means we assume that there is no viscosity of the fluid which is flowing. So there is no viscosity. The fluid which is having no viscosity is called ideal fluid. So there is no such fluid which is not having viscosity. So that is purely our assumption, and Euler and Bernoulli make this assumption. And when you make this assumption, we know that entire fluid friction is because of viscosity. So when I assume that there is no friction, no viscosity, there is no friction also, this particular then analysis becomes oversimplified analysis. So Bernoulli equation, Euler equation, whatever analysis you are doing, you are assuming that the flow is having no friction or viscosity, and hence the analysis becomes oversimplified. So non-viscous or inviscid is the second assumption of that. Third is incompressible. Incompressible. Now what is the meaning of incompressible? Density remains constant or change in density is zero. Don't say density is zero like inviscid. Inviscid mein viscosity is zero, but incompressible mein density is not changing. Density is remaining constant. We have already discussed that in the fluid, liquids are incompressible, gases are compressible. That means I only write this equation, that is Euler equation or Bernoulli equation, for liquids and not for the gases. So when I assume that density is constant, I am taking this equation for liquid. He will ask you to write the Bernoulli equation for gas, let us say air. I will tell you how that is also to be written. If he asks you to write the ideal gas equation, this equation for gases, you will say, sir, gases are compressible. So Euler Bernoulli equation we make assumption that density is constant, and hence we write that equation. But even if he asks you to write the equation for gas, you should be clear how it is to be done. Now fourth assumption is irrotational flow. Irrotational flow, that is the fourth assumption. Now what is the meaning of irrotational flow? When the fluid element is rotating about its own axis, it is said to have rotation, and rotation is a vector. It has three components. Let me give you a rotation about z axis, for which I remember this formula: curly v by curly x minus curly u by curly y divided by 2 is the rotation of the fluid element about z-axis. Similarly, there will be rotation of the fluid element along x-axis and about y-axis, and if I know these three components, I can calculate rotation of the fluid element. Now if I say fluid is irrotational fluid, that simply means omega x is 0, omega y is 0, omega z is 0. That means fluid is irrotational. Now these are the four assumptions in the Euler equation. and same are the assumption in Bernoulli equation. Now let me tell you, he normally he will confuse you with the giving one statement that is a uniform flow assumption of Euler equation and Bernoulli equation. Let me tell you, uniform flow means there is no change in the flow characteristic with space, or with change in length or change in space there is no change. That is called uniform flow. But a uniform flow is not one of the assumptions. So always remember, this is not the assumption. These are the four assumptions in the Euler equation which we are to basically use, and from there we are to analyze the fluid flow. Now from Euler equation I come to what is a very important topic, that is called Bernoulli equation. Now let me come to the part which is Bernoulli equation. Let me write that, and let me tell you, this Bernoulli equation is the energy conservation equation. As I told you, Euler equation is the equation of motion, where we study the motion of the fluid when it is flowing, velocity and all, because of some forces, that is dynamics. Bernoulli equation is the energy equation, and we consider we get Bernoulli equation from Euler equation only. When we integrate the Euler equation, we get the Bernoulli equation. Now let me write Euler equation first. dP by rho plus VdV plus G dz is equal to 0. That is the Euler equation. Now if I integrate this equation between two sections, I get Bernoulli equation. Now since fluid is incompressible, rho is assumed to be constant, it can be taken out, and hence this is 1 by rho, and integration of dP is nothing but P. So I can write it as P. If I say from 1 to 2, I say P2 minus P1 plus, what is the integration of VdV? You know that is V square by 2. So I write it as V2 square minus V1 square by 2 plus similarly Z2 minus Z1 is equal to 0. So I integrated between two limits, and this is what I got. Now what I do, I write all statements, all the terms which are at section 1 and I write on one side, and section 2 I write on the second side. So P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. See this equation carefully. If all these terms at section 1 are equal to all these terms at section 2, I can also write then P by rho plus V square by 2 plus Gz is equal to constant. I can also write these in this particular form. Now let me make some starting from here. This is the Bernoulli equation written in the simplest format. Now let me again write this Bernoulli equation here so that we make some analysis. I made a format of Bernoulli equation. P by rho plus V square by 2 plus Gz is equal to constant. I will say that this is the Bernoulli equation, but we know that Bernoulli equation is the energy conservation equation. So what kind of energies do we see here, and are these energies in the actual form or they are divided by something? Let's see here. We say that this one is the potential energy, this one is the kinetic energy, this one is the pressure energy. But you know one thing, potential energy is written as mgz, kinetic energy is written as half of mv square. But if you see these terms, they do not look like energies. That means these terms are not energy but divided by something, and that something is mass. Now if I ask you what do you think is the unit of this equation, you will say, sir, this equation is written in terms of kilojoule per kg, that if I multiply with the mass I am going to get energy. That means this equation is written in terms of specific energy. Specific energy means energy per unit mass. So we have got three energy terms here, that is the pressure energy, kinetic energy, potential energy per unit mass. I can say specific pressure energy, specific kinetic energy, specific potential energy, and the unit for that will be kilojoule per kg. Now sometime in the interview he asks you what is kinetic energy, you will say. What is the potential energy, also you will say. But suppose he asks you what is the pressure energy, then you are going to say, sir, pressure energy is equal to pressure into volume. And what is specific pressure energy? You will say, sir, specific pressure energy is pressure into volume over mass. So what is mass per unit volume? You will say pressure over density, and that is what we have written. So pressure over density is the specific pressure energy, kinetic energy divided by mass, potential energy divided by mass. This is the first format in which we have written the Bernoulli equation. Now let me tell you, Bernoulli equation is not normally written in this format. Bernoulli equation is written in some another format. And what is that another format is this? P by rho g plus v square by 2g plus z is equal to constant. Very, very important format for Bernoulli equation. So this was the first format, this is the second format. Can you tell me what is the unit of this? Now there is a principle called dimensional homogeneity principle, which is used in the basically fluid mechanics to verify the correctness of the equation which we have written. Now you see there are three terms here. Z is in meters. I can only add meter with meter with meter. I cannot add meter with meter per second. That means if the dimension or unit of this is meter, then dimension and unit of this is also going to be meter, and hence all the terms are written in meter and they have got specific name. This P by rho g is called pressure head. This is called pressure head and it is measured in meter. And I hope you remember, then hydrostatic pressure is calculated as P is equal to rho into G into Z. That means if you tell me that sir, water in the reservoir is up to 100 meter. So what will be the pressure? I will say pressure there will be rho into G into 100. That means the pressure corresponding to 100 meter of head can be calculated if I know the specific weight of the fluid. Rho G is called a specific weight. So if you give me the depth of the fluid or fluid up to what level you have stored, I multiply that with specific weight and get the what is the pressure up to that particular depth. This is called pressure head. Now similarly this is called kinetic head. This term is called kinetic head. Again it is in meter. And third term Z is called datum head. That is also calculated in meter. Pressure head, kinetic head and potential head or datum head. Now what is the unit of each term? Answer is sir, it is the meter. So this one is specific energy terms, this is the meter terms, head terms. Now out of these two equations, the equation which I have written just now in terms of head is more frequently used, and he is going to ask you why this equation, Bernoulli equation, normally is written in this format. And for that matter, of last couple of years he is also asking you the question, if you have only wrote memorized, agar apne you have crammed the formula, you may make the mistakes, because he will give you 4 choices and ask you which equation is correct. In this equation he will put P by rho plus V square by 2G plus GZ. Dimensionally it will be incorrect. So try to see whether dimensionally you are writing the right equation or not. This is something which is important. He will say P by rho G plus V square by 2 plus GZ is equal to constant. Again it is wrong. So you need to dimensionally see whether you have written equation which is right or not. In interview also it is very, very important to write Bernoulli equation and its units and dimension. Now one question he asks you is, why do you write Bernoulli equation in this second format most of the time? And you say, sir, this is because of the application. Later on I am going to tell you that this term directly you get from the hydrostatic pressure. P by rho G is nothing but pressure head. If I ask you 1 atmospheric pressure is equal to what? You say 0.76 meter of mercury or 10.3 meter of water. Now you see this particular data. I am asking you to tell me the pressure and you are saying meter of water. Meter is only unit of length, it is not unit of pressure. Then why you are saying 10.3 meter of water or 0.76 meter of mercury? That simply means that if you tell me this much meter of mercury, that means I know P by rho of mercury into G is 0.76. That means corresponding to 0.76, my pressure will be equal to density, roughly you know, for mercury is 13,600 kilogram per meter cube. And if I multiply now 0.76 with the specific weight of the mercury, I am going to get 100 kilopascal or 1 bar or 1 atmospheric pressure. That means P by rho G is a term which directly can be used in terms of meters, and this will give me the pressure corresponding to that particular depth for that particular fluid for which I am knowing the value of rho G. So practically speaking, this P by rho G term can be easily calculated if you give me the depth. And where do you see this? Let me give you the dam. Suppose there is a dam in which there is a water collected up to depth z. You can directly tell me that water is up to 100 meter head is there of the water. That means I know what is the pressure there. I know the pressure is rho into g into 100. Now from the dam you take penstock or a tube, and there is a nozzle which is attached to that penstock or the this particular pipe which you connected from the reservoir. What is the velocity of the jet which is coming from there? You say, sir, v is equal to root of 2gz, or v square by 2g is equal to z. Again I am calculating velocity of the jet in terms of the head. So all you need to calculate is head, and from that head you can calculate pressure also, from that head you can calculate the velocity of flow also, and hence this particular equation is important for us to write in this particular format. Later on I am going to tell you in the pitot tube, v square by 2g is nothing but kinetic head which you get in terms of difference of stagnation head and static head, and directly from there you get v square by 2g. So because of the application of each term used, this particular format of Bernoulli equation is very useful, and hence the format normally is used is in terms of head or various head terms in the Bernoulli equation. Now there is a third format also in which Bernoulli equation is written, and that format should be in kilowatt. This is kilojoule per kg, this is in meter. I want you to write one Bernoulli equation now in terms of fluid power or kilowatt. I want to know what is the fluid power. So can you suggest me how should I manipulate this to write in kilowatt? And what is kilowatt? Kilowatt is kilojoule per second. Can't I write it as kilojoule per kg into kg per second? You see, if in this equation I multiply with mass flow rate, I get the Bernoulli equation in kilowatt. So all you have to do is you have to multiply P by rho v square by 2 gz with mass flow rate, and assuming mass flow rate to be constant, and which is the continuity equation. So if mass flow rate is constant, that is continuity equation, I can write in this form. And how do you write mass flow rate? Mass flow rate is written as density into discharge, volume flow rate. So rho q g z is basically the fluid power. You get fluid power, and this is the third format in which equation can be written of the Bernoulli. So he's going to ask you to write Bernoulli equation in three format, and you remember all these three formats. This is the most important. After this comes, and this is important because this is related to the basically fluid power in the hydraulic machines. You are going to discuss about fluid power. So how the fluid power changes from one particular machine to another. From the fluid power it goes to your nozzle to blade to shaft. That entire transfer of the powers we are going to study in the fluid machinery. This is how we have to remember. Now after this I want you to memorize two things here. One is think of P is equal to rho gz. This is the hydrostatic law, that if I want to calculate pressure from some fluid or specific weight rho g and depth z, how shall I calculate that? You say P is equal to rho gz, and similarly power is equal to rho q g z, or I can say rho g q into z. Now these two formulas look like similar. Pressure is rho gz and power is rho q gz. So in this particular thing, specific weight which for water is 9810 SI units. This is density is 1000 and G is 9.81. So water it is 9810. As far as the QZ is concerned, what is Q? You will say, sir, Q is the discharge. Q is discharge, and what is Z? This is basically head. Now I will tell you that fluid will have power in it if it has discharge in it, or if it has head in this. On the basis of these two terms, we have different classification of fluid machineries. You must be knowing that there is a Pelton turbine, there is a Kaplan turbine, there is a Francis turbine. In case of Pelton turbine, we have high head. That means Z is more. Q is not more, but Z is more. In Kaplan, we have high Q. Q Q is more, discharge is more, Z is not there. In Francis we have both up to moderate level. So whenever we are to install some turbine or hydraulic machinery, we ask ourselves that in the fluid what kind of power is there. If the power is in the form of discharge or in the form of head, then we can get that particular power from there. So power has these two terms. Remember these two formulas, they are very, very important formulas. And remember that Bernoulli equation is written in these three formats, in terms of your specific energy, in terms of your head, and in terms of your fluid power. So these three formats you please remember. So we have already written a Bernoulli equation now. At two sections we have written Bernoulli equation. Let me give you some question. Let me see whether you can answer this question. Okay. I give you this pipe, which is a horizontal pipe. I am giving you two sections, and remember always Bernoulli equation is always applied at two sections which you choose. Choice is yours when you have to apply Bernoulli equation. Number two, whenever you calculate various terms on Bernoulli equation, these terms are calculated at particular streamline. He is going to ask you that question also in the interview, that where you are calculating P1, V1, Z1. So you are going to say, sir, I am taking one streamline, preferably in the center, and I am going to write the Bernoulli equation at the streamline at these 2 points. So let me give you this two sections. This is a pipe is horizontal, that means Z1, Z2, this is a datum. I mean datum from these two sections, these 2 points, from particular reference. I can take any reference, and from the reference I can measure what is a datum. Now because it is a horizontal pipe, then for the horizontal pipe Z1 is equal to Z2. Now let us say pressure here is P1, pressure here is P2, velocity here is V1, velocity here is V2, area is A1, area is A2. Now let me tell you one thing, whenever you are going to use Bernoulli equation, it is always to be used along with continuity equation. So continuity equation is something which you study in the fluid kinematics. And what is continuity equation? You will say, sir, continuity equation is mass flow rate conservation equation. That means whatever mass flow rate is entering at this section, same mass flow rate is going out of this section. That is called continuity equation. And how do you calculate the mass flow rate? Is rho 1 A1 V1 is equal to rho 2 A2 V2. That is the continuity equation we write. Now if fluid is incompressible, that is our assumption in Bernoulli equation. As I told you, assumption of Bernoulli equation are same as assumption of Euler equation. So if we assume that the fluid is incompressible, rho 1 is equal to rho 2. And if the pipe is of uniform section, if the pipe is of uniform section, then A1 is also equal to A2. These two are also equal. And from there we get V1 is equal to V2. So that means if the pipe is of uniform section, then our velocity is going to be constant, that is called uniform flow. So always make up a mind now that if a fluid is flowing in some passage or liquid is flowing in some passage where area of cross section is not changing, then the velocity also is not changing. That is called uniform flow, because to maintain continuous flow, continuity equation, you need to have uniform flow for that. So continuity equation is something which is like this. We got V1 is equal to V2. Now write Bernoulli equation. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. This is the continuity. This is the Bernoulli equation applied at two sections. Z1 is equal to Z2 because horizontal pipe. V1 is equal to V2, continuity equation. From there we get P1 is equal to P2. That means pressure also at the two positions is going to be same. Now the question is, if the datum is same, if datum is same at the section two sections, and if pressure is also same at two section, so fluid is made to flow either by datum difference, that is the gravitational potential, or pressure difference or pressure gradient. Neither there is a pressure gradient nor there is a datum gradient, datum potential. How the fluid is flowing then? He is going to ask you this question. You understood my question first? I am saying that fluid is flowing. Z1 is equal to Z2, that means the datum difference is not there, that means gravitational potential is not there, so fluid is not made to flow through gravitational potential. But P1 is also coming equal to P2, that means there is no pressure gradient also. Then what is making fluid flow? What is the dynamics behind that? And moreover, he is going to tell you that suppose I make manometer, I connect a manometer here. You know, manometer is the device which measures the pressure at two different sections. Suppose I connect a manometer in which there is a mercury kept like this, then the two limbs of manometer are showing some kind of difference. Mercury is not having same level. There is a level difference in the two limbs. Why this level difference is coming in the two limbs of the mercury? That is the question is going to ask you. That means certainly pressure P1 is more than P2, but Bernoulli equation is not going to give you that. Why it is not there? Now the reason or the answer to all these questions is that the Bernoulli equation which we have written, actually that equation is written for ideal flow, or that is for inviscid fluid, for which we have assumed that viscosity is not there. Viscosity is basically zero in such fluid, but actual में viscosity is not zero. There is viscosity and there is a fluid friction, and hence friction will be involved. That means how shall we write now Bernoulli equation for real fluid? How shall we write Bernoulli equation for real fluid? So this is something which is very, very important. This is called Bernoulli equation for real fluids. How do we write Bernoulli equation for real fluids? Let me now write this equation for you. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF. Now think of this term. This HF is called head loss due to friction. This is called head loss due to friction. Now remember this is the equation for Bernoulli, and this head loss is basically because of viscosity of the fluid. When I am going to discuss with you viscous flow, I am going to tell you that there is an equation called Darcy equation or Hagen-Poiseuille equation, which is used to calculate this value of HF. This HF is coming out to be 4FLU square over 2GD, where F is called coefficient of friction. Darcy equation you are going to do there you are going to learn how to calculate HF and how to calculate the loss of head, and this F is coefficient of friction, which actually is dependent upon the Reynolds number of the flow, and Reynolds number depends upon the viscosity. So because of viscosity some energy is going to be lost. Anyhow, forget about this, just think of this is a head loss due to friction, and since everything is written in meters, head loss is also in meter of the fluid. Now in the Bernoulli equation, all these three energies, pressure energy, kinetic energy, potential energy, these are called conservative energy terms. Conservative energy terms. That means conservative energy at section 1, conservative energy at section 2, and this is called non-conservative energy. This is called non-conservative energy term. That means total energy is conserved. Total energy is always conserved, but total energy is made up of two parts: conservative, non-conservative. What is the meaning of conservative? Energy which you can conserve. English word conserve. That means you can store at particular point. If I give you this duster, this particular thing has a potential energy. Where is this? That is stored in this, because it has mass and it is kept at some datum. It has a potential energy. If I release it, that potential energy is going to get converted into kinetic energy. Fan is rotating. Now this fan has kinetic energy in that. Where is that? That kinetic energy in the fan is in the form of its RPM or rotational speed. Half of I moment of inertia into omega square is the kinetic energy of the fan. Fan has moment of inertia and fan has a rotational speed in radian per second. It has a kinetic energy. So that means energy which you can store is called conservative energy. Football has pressure inside it. It has energy inside this. Dam has hydrostatic pressure in it. It has a pressure energy in it. Kinetic energy, fan example I gave you, potential energy I gave you example of this duster. So that means these energies can be stored at particular place. Now think of friction. Energy which is involved in friction, you cannot store that at particular point. You cannot store that energy in the system. Hence those are called non-conservative energies. So whenever he asks you to write Bernoulli equation for real fluid, you write it in terms of energy loss or head loss. Now this is the only equation, listen to me carefully, which can tell you the direction of flow of fluid. Conservative energy terms cannot tell you direction of fluid flow. Whenever I ask student that okay, I am giving you this particular section of pipe, let us say section 1, section 2, and let us say this pressure P1, pressure P2, and this pressure at P1 is more than pressure at P2, and when I ask student tell the direction of flow, they tend to give answer that sir, pressure here is more, pressure here is less, so fluid is going to flow from high pressure to low pressure. That is wrong. Fluid flows both from high pressure to low and low to high pressure. Think of turbine. Turbine में fluid is flowing from high pressure to low pressure. Think of pump. Pump में fluid is flowing from low pressure to high pressure. Whenever I ask students that let me give you this pipe, section 1, section 2, tell me from where fluid is flowing to which direction. They say, sir, from 1 to 2. Why? Because sir, 1 is at high datum. Wrong answer. Fluid does not always flow from high datum to low datum. It can be reverse. When you are filling the water in the tank at the roof, fluid is flowing from low datum to high datum. That means how to know the direction of flow? Direction of flow can only be calculated if you calculate all these conservative energies at section 1 and all these conservative energies at section 2, and then you calculate HF. Now if HF is coming out to be positive, then fluid flows from 1 to 2, and if HF is coming negative, that means fluid is flowing from 2 to 1. Always remember this. That means if all these energies here is more than all these energies here, that means some energy is lost, and that energy is lost because you have gone from 1 to 2. Suppose these energies are more than this energy terms, conservative energy terms, that means fluid has gone from this side to this side, because it is a common sense. Suppose I am at this point now, I walk for a while, friction takes place, the friction is going to eat some energy. That means my conservative energy at section 1 was more than section 2. Suppose I drop this particular body here, its potential energy gets converted into kinetic energy when it hits the surface, but entire potential energy will not convert into kinetic energy. Some energy is lost in the air drag. So that means energy at section 1 was more than energy at section 2. If energy at section 1 is more than energy at section 2, this is going to be positive, and hence direction of flow is 1 to 2. But if direct energy at section 2 is more than energies at section 1, conservative energies, then direction of flow is 2 to 1. That is the only parameter which is going to tell you how the energy is going to flow, what is the direction of flow, that is only going to tell you that. Later on I will discuss with you that there is a terminology used for these conservative energy terms, that is called energy gradient line. Energy gradient line includes all these three terms, and then there is a hydraulic gradient line. In hydraulic gradient line, only these two terms come. These are also called piezometric head. So hydraulic gradient line is this, energy gradient line is this. That means energy gradient line actually tells you the direction of flow, the direction in which energy gradient line slopes down, that is basically the direction of flow. So let me summarize now. How to write Bernoulli equation for real fluid? You need to calculate the head loss or friction loss. How to know the direction of fluid flow? You need to calculate conservative energies at two sections, see where it is more, and the direction of flow is from high conservative energy terms to low conservative energy terms. You know, sometime he asks you to write Bernoulli equation for a pump and turbine. Let me tell you what is the meaning of that. Let me give you a pump, and maybe you know that pump is the device in which you do the work and give the energy to the fluid. Let us now say fluid was flowing from section 1 to section 2, let us say this, and there is a pump involved in between. Fluid is going to flow from 1 to 2, and there is a pump here. That is the meaning of it. Now let us write all energy terms at 1. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF. HF is the head loss when the fluid flows from 1 to 2. Now where shall you add pump work? Now you know one thing, this was the conservative energy at section 1, plus I did some work, I gave energy to the fluid. That means when I gave energy to the fluid, energy at section 2 will be more. That means where shall I add the pump work? I shall add pump work at this point. Forget about friction. Suppose there is no friction, and I ask you a question, energy at 1 is more or energy at 2 is more? I was having energy at 1, this is this energy, and then I got some more energy that is to be added, and then I have more energy at section 2. So if I forget about friction loss, then energy, conservative energy at 2 is conservative energy at 1 plus pump work. So if suppose there is a pump in the fluid flow direction and he has given you all these terms, then difference of all these terms is the pump work. That is what you should write. Now turbine is the device which is reverse of pump. That means turbine is used to extract work from the fluid flow. Let me give you some diagram of the turbine also. Let us say there is a turbine flow and the fluid enters here, turbine does some work, and then fluid goes here. Section 1, section 2, turbine work. Turbine is centrifugal mechanism. So let's say the shaft and the blades are mounted on that. This is how the turbine is installed. Now how to write equation? P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Now can you tell me where should I add the turbine work? Now what I was knowing here is I am having some energies here, out of which some energy is extracted and then the rest energy is released. That means W turbine plus this is equal to this particular thing which is at section 1. Let's say this is section 1. So this entire energy is equal to this energy plus turbine work. That means turbine work is to be added here. And if there is a head loss of fluid friction loss, then you can write HF here. So maximum number of times is going to tell you or ask you to write the Bernoulli equation for pump and turbine, how this equation is to be seen, how this equation to be understood. So turbine and pump के लिए Bernoulli equation, loss के लिए Bernoulli equation, direction of flow how you will understand. These all questions he is going to ask you. Now I want you to understand a small concept related to pressure and change of pressure. This is a term which I want to clarify you. Change in pressure or pressure gradient. Change in pressure, also called pressure gradient. This is a term that means change in pressure, and there is a term related to that which is called P1 P2 minus P1 by rho g. This is either called difference of pressure head, this is called difference of pressure head, or this is called loss of pressure head, loss of pressure head. Now remember, this loss term is related to fluid friction or viscosity, and that is for real fluids, and this term is called HF. That is what we have written. So pressure changes either because of friction, that is called loss of pressure head, or that is called HF, and that is because of viscosity, or pressure changes because some another factor, not friction but other factor, that is called difference of pressure head. And both the terms are written as P1 minus P2 by rho g or P2 minus P1 by rho g, whatever you call it. I'll discuss that. So this difference of pressure head, how it is to be calculated, and why friction always decreases the pressure. Because in Bernoulli there are three energy terms: kinetic energy, potential energy, pressure energy. Why friction will always decrease pressure energy? Why not kinetic energy? Why not datum or potential energy? Let me discuss that now. Let me give you a horizontal pipe. I discussed just now with you this particular case, and let's consider the actual fluid flow. Let's say fluid is flowing from section 1 to section 2. The fluid is flowing from section 1 to section 2. If the pipe is horizontal, Z1 is equal to Z2. If the pipe is of uniform section, V1 is equal to V2. If Z1 is equal to Z2, V1 is equal to V2, how do we write equation? P1 by rho g, V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HF. Now Z1 is equal to Z2, V1 is equal to V2. Can you tell me what is HF? P1 minus P2 by rho g. And let us say through manometer I came to know that limb difference of mercury is like this. Study the manometer properly. And this limb difference is telling you that P1 is more than P2. So why P1 is more than P2? And if P1 is more than P2, HF is positive. And if HF is positive, fluid flow direction is this. That simply means this pressure loss, this is the actual pressure loss because of friction. So this difference of pressure head is called friction, loss of pressure head because of friction and because of viscosity. Suppose the limb difference is this side, limb difference is this one. Mercury goes this side more. That means pressure P2 is more than P1. And if pressure P2 is more than P1, this HF is negative. And if HF is negative, you know direction of flow is from 2 to 1. So in this case, the pressure loss or the difference of pressure was actually the pressure loss because of friction. Friction eats up pressure. Why friction only eats up pressure? Reason for that is datum is independent. Datum does not depend upon anything. Velocity is maintained constant because of continuity equation. Continuity equation is to be satisfied. Then third energy term is the pressure energy, which actually is reduced because of friction. Why? Because friction is viscosity. Viscosity is intermolecular attraction. Pressure is because of intermolecular collision. Now let me ask you a question. If the fluid has more viscosity or more intermolecular attraction, do you think there will be more intermolecular collision? Answer is no. That means if fluid has more viscosity or more intermolecular attraction, then the pressure will be reduced or intermolecular collision will be reduced. So you can make some kind of rough idea in your mind that whenever there is a friction, that friction is going to eat the pressure energy is going to decrease. This is something which is very important. Now let me give you another variation or change of pressure. Let's first not consider the friction. I am giving you here two sections. Let us say section 1, let us say section 2. Section 1, section 2. As is very clear, A1 area of cross section is more than A2. And let's go for continuity equation. If I think of continuity equation, then rho 1 A1 V1 is equal to rho 2 A2 V2. I told you earlier also, continuity equation means conservation of mass flow rate. Mass flow rate at section 1 is equal to mass flow rate at section 2. That is called continuity equation. Mass flow rate is rho 1 A1 V1 is equal to rho 2 A2 V2. And if I am assuming fluid to be incompressible, that means rho 1 is equal to rho 2. If rho 1 is equal to rho 2, and then A1 V1 is equal to A2 V2. Now as we know, A1 is more than A2. Cross section A1 is more than A2. That means V2 is more than V1. So V2 is more than V1. That means velocity of flow at section 2 is more than section 1. Let's now go for Bernoulli equation. Let's write Bernoulli equation. When we write Bernoulli equation, this is what is happening. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. I am not considering friction as of now because I want to see how the areal change in area of cross section is going to change the pressure. Now Z1 is equal to Z2. I told you the datum is the independent variable. It does not depend upon kinetic energy or pressure energy. It is basically head at which the surface is contained. So Z1 is equal to Z2, horizontal pipe. Now A1 is more than A2, so V2 is more than V1. If V2 square by 2g is more than V1 square by 2g, don't you think P1 by rho g is more than P2 by rho g? See this equation. In this equation, let me remove Z1, Z2. Now see this equation. If this energy is more, V2 square by 2g is more, that means P2 by rho g is less because both sides it is equal. That simply means if A1 is more than A2, then V2 is more than V1 and P1 is more than P2. You see now these three correlations, and this correlation tells you, and you know what, this velocity is not decided by anything but continuity equation, and continuity equation says then that when area is less, velocity is more, and then next version is Bernoulli equation. If area is more, pressure is more. You see this, A1 more than A2, P1 more than P2. So what I am going to do is, now suppose I am going to connect the manometer at two sections. Suppose I do that, then you know what, the limb difference will be something like this. Limb difference will be something like this. That means P1 is more than P2. So now I want you to understand one thing here. Change in pressure. Change in pressure is called difference of pressure head also. It is called loss of pressure head also. Pressure changes whenever there is a change in area. That is called areal gradient. And always remember in your mind that pressure will be more where area is more. Pressure will decrease if area decreases. Why pressure decreases with decrease in area? Because sir, as the area decreases, velocity increases, pressure energy decreases. So that is the relation between area and pressure. But many times students say, sir, dimensionally pressure is force per unit area. Pressure is equal to force per unit area. That means pressure is inversely proportional to area. That means if area is less, pressure is more. If area is more, pressure is less. That is what the question they ask. Let me tell you, first thing, this particular expression is dimensionally written. Why? Because pressure is Newton per meter square. But I tell you one thing, actually this is written like this. Actually it should be written like this. Why? Because in this formula, pressure is input and force is output. Have you not done hydrostatic pressure? Have you not calculated hydrostatic pressure force on submerged bodies? In that particular case, first pressure comes and then pressure force comes. So I will say that the pressure is input and pressure force is output. It is not the other way around. Pressure is the independent parameter. Pressure is because of intermolecular collision. It does not depend upon the force. Hence, you should always know that this particular formula is used to calculate force, not pressure. Number one. Number two, why pressure is related to area? That is related to area because of energy. When kinetic energy is less, pressure energy is more. And from there you make a correlation that during the fluid flow, if area increases, and we have to make the conservative energy conserve, we have to equate that, then as the area increases, pressure also increases. Make that a thing in your mind. Plus always remember that pressure changes because of two things. One is because of friction. Friction always eats the pressure, that is called loss of pressure head, and that tells you about the direction of flow. And another thing is pressure changes because of area, where area is more, pressure is more. These three things are very, very important for us to know. So I believe we have discussed about Euler equation, Bernoulli equation, assumptions, how to apply Bernoulli equation across pump and turbine, and how to know the direction of flow from the Bernoulli equation by finding the conservative energy terms, and what are the various energy terms in Bernoulli equation and their units, and what are the three formats in which Bernoulli equation is written. Now let me discuss with you how Bernoulli equation is to be used to calculate certain energy terms. Let me give you some simple examples here. Simple examples. He will give you that suppose there is a tank in which fluid is kept up to depth z. Tell me what is the velocity at the exit. Very, very simple question. Always remember that you have to use the Bernoulli equation, or you have to find the sections depending upon what is asked, what is the question actually. So he's saying what is the velocity here, and you know the certain parameters at section 1 and section 2. Let me ask you, what is the pressure here? You will say, sir, atmospheric pressure. What is pressure here? Atmospheric pressure. What is the datum here? Let us say Z1 is equal to Z. And what is datum here? Let's take it reference. That means Z2 is 0. What is velocity here? We assume velocity here almost 0. And what is velocity here? That is to be obtained. So let's go for this equation now. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. I am neglecting the fluid friction here. Now let's say P1 and P2 get cancelled out because both places pressure is same, that is atmospheric pressure. Let's neglect V1 also, because in comparison to V2, V1 is very, very small because area of cross section is very large. So this surface may velocity will be very less. Now let us say Z1 is equal to Z and Z2 is reference. What do we get is root of 2gz is the velocity of flow, velocity of the jet. But you know what? Whenever fluid flows, there is some kind of change in direction or minor losses. Those minor losses are basically catered to by putting some parameter which is called coefficient of velocity. So he will give you some coefficient of velocity for the nozzle or that particular tip and through which the fluid is going to flow. So V2 is equal to CV root of 2gz. That is the fluid flow through this particular section. So this is how it is to be obtained. Now let me change this question little bit and see whether you can answer my question now. Let me give you now this particular part. Okay, I give you now this question. Fluid is up to this, let us say Z1. This is the fluid surface, and fluid is going to come out of this particular tip in the form of jet, and let us say this is at height Z2. Now how to find out velocity? We can find out velocity again by putting Bernoulli equation at these two sections. Do I know pressure at section 1? Yes, P atmosphere. Do I know pressure at 2? Yes, P atmosphere. Do I know velocity here? Yes, V1 0. Do I know velocity here? I want to calculate it, V2. Do I know Z here? Yes, Z1. Z here, Z2. Yes, I know that. Let's write Bernoulli equation. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2, neglecting the friction. Now P1, P2 gets cancelled out. Now V1 is almost 0. What is V2? Is root of 2g Z1 minus Z2 under root. And let me coin a term here. Z. What is Z? Z1 minus Z2. So that term again comes out to be 2gz. You know, very interesting thing. That means the velocity of flow through this jet will only depend upon what is the datum difference between this surface and from where the liquid is coming, and hence I want to find out velocity at the jet velocity can be obtained at this particular point, root of 2g z1 minus z2. Now what if I increase z2 to the size of z1? Suppose I take it forward, no fluid will come out. So you must have observed that if your house is on the top floor, second floor, first floor, tank is on the roof, then maximum velocity of flow will be at the bottom or ground floor. Then minimum velocity of flow because of the tank at roof will be at the top floor. Why? Because datum is different. This is how you have to understand this. Let me ask you a very simple question here. What do you think will be the velocity at point A? What will be VA? Can you answer that? What will be velocity at point A? Just answer me that question. I told you velocity at this point, V is root of 2gz. Z is this difference. What is velocity here? Now use continuity equation. If area of cross section of this tube everywhere is same, if area of cross section of the tube everywhere is same, then velocity also everywhere is going to be same, because continuity equation has to be followed. Mass flow rate is conservative, mass flow rate is constant, mass flow rate through this, mass flow rate through is constant, a1 v1. So whatever velocity you have calculated here throughout the pipe, velocity is going to be same. Remember that always. Now if I club these two things together and give you this question, let me see whether you can answer that. I am giving you now two tanks. Let us say this is tank 1, this is tank 2, and let us say there is a fluid up to datum z1, and let us say the fluid is up to datum z2 here. Can you tell me what is the velocity of flow here? Velocity of flow here. Now we have understood a thumb rule that the velocity of flow will only be because of datum difference. You understand that? Datum difference. So z1 minus z2. What is the datum difference? You say, sir, z is z1 minus z2. What is the velocity? Sir, root of 2gz. That is 2g z1 minus z2. That is the velocity of flow through here. This is how we calculate or use this concept to calculate velocity of flow when two containers of particular area or cross section are basically joined. This is how we are to calculate the velocity of flow. You know, I give you a practical problem which in the ancient days people used to use this particular solution. Let us say this is a lake. Let us say this is a lake having water here, and let us say my house is on the other side of a mountain. This is the mountain. This is the mountain, and my house or my village is this side. This side, on the other side of the mountain, there is a lake. Now I want to bring water from the lake to my house. Let's use Bernoulli Equation. One thing is I climb the mountain every day and bring the water from the lake and bring my house, but that is very troublesome, as you know. So a lot of hard work is involved. Now what I do, I lay a pipe here. I laid a pipe here. Let's say this is the pipe. All I know is that if my village is at datum z, the lake water is at datum, let us say z. Lake is at datum z above my village. Now let's go for Bernoulli equation. What is pressure here? Atmospheric pressure. What is pressure at the exit of the pipe here in my village? Atmospheric pressure. What is velocity here? V1 0. What is velocity here? V2. I want to calculate. What is datum here? Z. What is datum here? 0. Again the same thing. Don't you think if I use the Bernoulli equation, I am going to get root of 2gz. Root of 2gz is the velocity. That means if I lay a pipe between lake and my village through the mountain also, then eventually it is going to matter only how much is the head available in the lake compared to my village, and I am going to get this as the water. But you know, this equation which I have written for Bernoulli, this is the equation for ideal fluid. For the real fluid, you know how equation is written? And by the way, let me first answer this question. If he asks you what is the velocity at point 1 in the pipe, that will be same as root of 2gz. Why? Because continuity equation says everywhere velocity is same, because everywhere area of cross section is same. So velocity is going to be same. Now this equation which I wrote and I calculated was for ideal or inviscid flow. How do you write equation for, let us say, real fluid is equal to this, V2 square by 2g plus Z2 plus HF. Now say pressure both sides is the same, done. Velocity is 0, done. Let us say Z1 is Z, and Z2 is 0. Now let's see what is V2 square by 2G is equal to Z minus HF. What is V2? 2G Z minus HF under root. You know V2 will be positive only if Z is more than HF. And you know what is HF? HF is the head loss. When we discuss how head loss is to be calculated in the pipe through Darcy equation, first thing you have to do is, suppose this pipe is 100 meter long, or let's say 1 kilometer long, you have to calculate the head loss in the pipe. And if head loss in the pipe is less than the head available, then only fluid is going to flow. So if you even lay the pipe, if you're a civil engineer, you lay the pipe, first you calculate what is going to be head loss in this. If you calculate head loss, then only you will be in position to tell whether the head available is more than the head loss going to be or not. If head available is not more, then fluid is not going to flow because of the friction. But suppose head available is far more than head loss, then obviously it is a very good thing for us. We can get water if we lay the pipe across the mountain. So how HF is to be calculated? There is a viscous flow. You will see the Darcy equation, Hagen-Poiseuille equation. You can calculate that. Interview may also this question is asked whether I can get the fluid flow or not. That is something which is to be calculated. Fine. So I hope this concept is clear. Okay. So let me discuss now with you some more devices which are based upon Bernoulli equation. Three main devices which you should know. One is called Venturimeter, then Orifice meter, and third is called pitot tube. These are the three devices which are based upon Bernoulli equation. And let me tell you, Venturimeter and Orifice meter both are the devices which are used to measure discharge, which we call Q, and pitot tube is used to measure velocity. But you know, we know that this discharge is area into velocity. This velocity is basically average velocity, but the velocity which pitot tube measures is not average velocity. It is the velocity where you put the pitot tube, and discharge is area into that average velocity. So if he asks you, can't I use pitot tube to measure discharge, because velocity it is measuring, area into velocity will give you discharge. You will say, sir, area into velocity is discharge, but that velocity is average velocity. If you know average velocity, you can measure discharge. If you say you can measure discharge, can't you measure velocity? You say yes, I can measure velocity, but that velocity is going to be average velocity. So these are the devices which are based upon Bernoulli equation. Now let me explain you the concept of each of these devices. First of all, we go for Venturimeter. It's a very important device, Venturimeter. Let me explain this Venturimeter to you. What is actually Venturimeter is this. Let me give you a pipe. Suppose I want to measure what is the flow rate or mass flow rate through pipe. And pipe is closed. How shall I measure the mass flow rate through the pipe? What we do, we cut this pipe. We cut this pipe at particular section, and we insert Venturimeter into this. Now what is Venturimeter is? Venturimeter is actually a converging throat diverging section pipe. Now let me make the diagram here. Let us say this is the pipe, and if I can use a different color to show how Venturimeter is to be connected. Okay, now this is Venturimeter for me, and these are the two sections of pipe. So what pipes I have cut, I have separated this one section, another section, and introduced this Venturimeter. So what is Venturimeter? Converging throat diverging section. Then what we do is this, we put a manometer, in the Venturimeter, something like this. We connect manometer with this. This is the throat section of Venturimeter, and this is the pipe, and we want to find out the discharge through pipe. So let us say this section is 1, this section is 2, section 1, section 2, and in the manometer there will be fluid, let us say mercury, having density rho Hg, and let us say the fluid which is flowing is having density rho. So somebody asks you, what is Venturimeter? Sir, Venturimeter is a converging throat diverging section. Why there is a throat? Because I want to minimize area. Why I want to minimize area? Because if area is minimum, velocity is more. Velocity is more, then pressure is less. So you know, pressure here is more, pressure here is less, and that particular difference in pressure can be represented as in the limb difference of this particular fluid, which is mercury. Now let us see how venturimeter is to be used to measure the discharge. What I do here is I use continuity equation between section 1 and 2. When I use continuity equation, let us say continuity equation between section 1 and 2, I get A1 V1 is equal to A2 V2. I am assuming rho 1 is equal to rho 2. So A1 area at section 1, A2 area at section 2. Area of section 2 means area of the throat, A1 means area of the pipe. And from there what I do, I write V1 as A2 by A1 into V2. I am going to use this velocity V1 in terms of V2 in some equation. Now let us write the Bernoulli equation between these two sections. When I write Bernoulli equation between two sections, P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. This is the Bernoulli equation between two sections. Now let us say Z1 is equal to Z2 because this orifice meter, this venturimeter is a horizontal, let us say. Now let us say P1 minus P2 by rho g is equal to V2 square minus V1 square by 2g, and let us say that is small h. Now what is small h? Small h is the difference of pressure head. This is not a pressure loss of pressure head, this is not loss of pressure head, this is difference of pressure head. What is the difference of pressure head? Difference in pressure because of area change. So here area is more, pressure is more, area is less, pressure is less, and that difference in pressure is because of area change, which I can measure in terms of velocity. Now we will calculate what is h using manometer. We will calculate that also, but before that let's go for this expression. Now V2 square minus V1 square over 2g is equal to h. Let us say that. Now what I do, V2 square minus V1 square I can measure as equal to root of 2gh. Now what I do, I express V1 in terms of V2. V2 square minus A2 by A1 whole square V2 square is equal to 2gh. Now from here what I get is V2 is equal to, let's take certain things common. V2 square I take common. A1 square minus A2 square over A1 square is equal to 2gh, and from there I got V2 is equal to A1 square, V2 square is equal to A1 square, A1 square minus A2 square into 2gh. Now if I take under root, then what I get here is, this is the value which I get. V2 is equal to A1 or A1 square minus A2 square under root into root of 2gh. But we want to find out discharge, and you know what is discharge? Discharge is A2 V2 or A1 V1. If I put that value, A1 A2 over A1 square minus A2 square into root of 2gh. That is the value of discharge. Now you see the beauty of this expression. In this expression, all the terms are known to us. A1 is the area of cross section of the pipe, A2 is the area of cross section of the throat, and H is the difference of pressure head, which I am to measure through this. That I will tell you how to measure. This is the discharge which we wanted to calculate. Let me erase certain things here. Now this is the formula we have got, which you have to remember, that discharge through venturimeter is A1 A2 over A1 square minus A2 square root of 2gh. That is a discharge. But you know, this is the theoretical discharge. The actual discharge is to be obtained by considering some losses because of the change in area. So actual discharge is equal to CD A1 A2 over A1 square minus A2 square under root of 2gh. This is the actual discharge through venturimeter. You need to remember this formula, and whenever A1 A2 is given to us, H is given to us, H is limb to be calculated from limb difference, H is difference of pressure head, then we can calculate what is the value of this particular discharge through venturimeter. Now how to find out H? We know H is nothing but P1 minus P2 by rho g. That is value of H. And how shall we find out difference P1 minus P2 by rho g? Let's try to use the manometric concept. Let us say this difference is x. This difference is x. Now I take section A and I take, let us say, section B. Pressure at A is equal to pressure at B. Same fluid, same level. So pressure at A is equal to pressure at B. Now let's go from here. P1 plus rho g x plus y. Rho is the density of the fluid, hydrostatic law lagao, P1 pressure at this point plus rho g, this entire distance. How much is this distance? X plus y is equal to, now let's come this side, pressure at this point is P2 plus rho g x plus rho mercury g y. So let me write it, P2 plus rho g x plus rho mercury g y. Now you understand, rho g x gets cancelled out, and P1 minus P2 will be equal to rho mercury minus rho into g into y. But we want to find out P1 minus P2 by rho g, and how that is obtained. P1 minus P2 by rho g, which is small h, is equal to rho mercury minus rho over rho into y. G will get cancelled out. This comes out to be rho mercury by rho minus 1 into y. Now that means this value of h is nothing but rho mercury by rho minus 1 into y. Instead of density, I can also write this expression in terms of specific gravity. That means specific gravity of mercury over specific gravity of the fluid which is flowing minus 1 over y. All I need to do is I need to divide rho mercury and rho with rho w, rho water, and then I'm going to get specific gravity of these two fluids. So that is going to give me h value which I want to put. All you need to remember is, you need to remember this discharge formula, and you need to remember that in this discharge formula you need to calculate h in terms of fluid which is flowing. Now if you are very good and if you are comfortable with the manometers, you know that there can be inverted U-tube manometer also, and you also know why inverted U-tube manometers are used. If the pressure difference is not very high, then you go for inverted U-tube manometer. In that case, you are going to get this kind of diagram, you see, and fluid, let us say, has density rho s in that particular thing, and let us say this difference is coming out to be y, any distance y. Then in that case the value of small h will come out to be 1 minus rho s over rho into y. So for U-tube manometer, density of mercury is more than density of this fluid. For inverted U-tube manometer, density of the fluid is going to be lesser than density of the flowing fluid. Density of this fluid, that is in the manometric fluid, is going to be lesser than density of the fluid which is flowing. So this will be 1 minus something. This in this side it will be rho mercury by rho minus 1. This is 1 minus rho s over rho. So these two formulas you should think of. Why do we use U-tube manometer if the pressure difference is very high? Why do we use inverted U-tube manometer if pressure difference is less and not very high? This is how we are going to use the formula to calculate discharge through Venturimeter. Now you see, if I do not take horizontal manometer, horizontal Venturimeter, if I take inclined manometer, let us say like this, if I take inclined manometer, how my formula is going to change? And suppose I use this as the manometric limb difference is obtained like this. Let us say this is what is the diagram for me. This is section 1, fluid is going to flow P1, P2. Now let us say the difference, datum difference between two is z. So if I take the pipe which is inclined pipe and I take inclined manometer, inclined Venturimeter, not horizontal Venturimeter, how this formula is going to get changed? In that case, there is no difference in the formula. If you derive entire expression again, which I am not going to do for you, that is not required, but you remember simply one concept here. Even if the Venturimeter is inclined, even then discharge ka formula is going to remain same. Whatever formula we have seen, it is going to remain same. How we are going to find h is, h again is rho of mercury by rho minus 1 into y, where y is the limb difference. That has to be vertical actually. This y has to be vertical, and this is again going to be the same formula. So if you derive the expression of this, you are going to find the same expression is going to come. That you please remember. This is something which is very, very important. Now this is something which we have done Venturimeter, and Venturimeter mein we find the discharge at through the pipe, and discharge also gives you velocity, but that is the average velocity. Now what is orifice meter? Let me tell you, orifice meter is exactly similar to Venturimeter. Need not to go in detail of that. Orifice meter is similar to Venturimeter. The only difference is in the Venturimeter you introduce a venturi, that means converging through diverging section pipe. In orifice meter, what you introduce is the orifice. So what is the orifice? Orifice actually is a circular plate with concentric hole. So if I make the cross section of that, there is a plane section in which there is a basically concentric hole. So fluid is going to flow something like this, because when you create some kind of obstruction, then the streamlines are going to flow like this. Because of obstruction created here, minimum cross section area, let us consider the cross section area of this venturi is this, and whole area cross section is this. Let us say pipe ka cross section area is A1 and minimum cross section area is obtained of the jet little downstream of this particular orifice, and this particular part is called vena contracta. This is called vena contracta. It is not an English word. Let me tell you again. When the fluid flows, because of obstruction of this orifice, the fluid flow lines or streamlines are going to follow some path, and the minimum cross section is hit little downstream of this particular orifice, and hence the cross section there is minimum, that is A2. Now what we do here is we put the manometer, one limb of the manometer is put in the pipe, and another limb of the manometer is put where cross section is minimum, and that minimum cross section of the fluid flow is obtained at some distance from the orifice because of inertia of the streamline, that is called vena contracta. Again pressure here is more, and pressure, because area is less, velocity is more, pressure here is going to be less, so we are going to get this kind of manometric limb difference. Let us say this difference is y. And again the formula of discharge is going to be CD A1 A2 over A1 square minus A2 square under root of 2GH. And how H is obtained? Again rho mercury by rho minus 1 into Y. So as you can see, same formula, we are going to get same formula with the only difference that how shall you measure A2? Minimum cross section area cannot be measured. But then there is something which is called coefficient of contraction. Coefficient of contraction. What is coefficient of contraction is A2 over A0. What is A0? A0 is cross section area of the orifice. So we know A1, we know A0. If coefficient of contraction is given, we can find out A2 in terms of A0. A0 is known to us, so A2 will also be known to us. So in terms of coefficient of contraction, I can find out A2 and I can put that formula there, and exactly same expression for venturimeter and orifice meter. Now the question comes is, why you will go for orifice meter if venturimeter is already there? What is the need of orifice meter? And the answer for that is, this orifice meter is a very simple device. It is a simple device because it is only a plate in which you have a concentric hole. That is orifice meter, plate with concentric hole, and through which fluid is going to flow. And second thing is, it can be easily inserted. Maintenance is not a problem, but venturimeter was a pipe converging through diverging section pipe. Second is coefficient of discharge. Coefficient of discharge for orifice meter is lesser than venturimeter. You know, if coefficient of discharge is 1, that means it is very efficient. If coefficient of discharge is 1, that means there is no loss. So coefficient of discharge for orifice meter is lesser than that of venturimeter. That means this is not efficient device. Venturimeter is efficient device, orifice meter is not efficient device. That is the one difference between two. And hence, if he asks you why you will go for venturimeter not orifice meter, answer for that is, sir, orifice meter is not a efficient device. It is simple, cheap, easy to maintain, but it is not efficient. Why? Because losses are more. Why losses are more? Because there is a sudden change in cross sectional area. In orifice meter, change in cross section area was not sudden. Why? Because there is a converging section, then throat comes. But in this case, sudden change in cross sectional area, because of which there is a sudden change in direction of streamlines, because of which losses are more. And that is the main difference why we go for orifice venturimeter instead of orifice meter. Formula is same, all analysis other is same. CD value for this is lesser than that of venturimeter. That is what we need to remember. Okay, so let's go for pitot tube now. Third thing is pitot tube. Now if somebody asks you why pitot tube is used, it's a very catchy word. No, pitot tube is catchy word. So normally this is asked in the interview. So what is pitot tube is? Sir, pitot tube is the L-shaped glass tube which is used to measure velocity of flow at particular point. Section nahi. Whatever velocity of flow you are measuring at a section, that is a average velocity which you have measured using Orifice meter and Venturimeter. Whatever velocity you are measuring at a point is called instantaneous velocity, I think, and that is measured with pitot tube. So pitot tube is a glass tube which actually is used to measure the velocity of flow at that particular section. Let me give you a pipe, and since pipe has a pressurized flow, if I join a piezometer, you must be knowing what is piezometer. Piezometer is basically glass tube which is a simple tube. If you insert that glass tube in the pressurized chamber, then the liquid comes out. So if there is a pressure in the let us say P1 is the pressure at the section, and if that pressure is more than atmospheric pressure, then it is going to come out. Let us say small h is that particular pressure. You know, pressure here is P atmosphere. So what will be pressure here, or entire full section? I will say hydrostatic law. P1 is P atmosphere plus rho g into h. Let us say rho is the fluid which is flowing. This is the concept of piezometer. Now if I assume this to be 0, then P1 is the gauge pressure. It is not absolute pressure but gauge pressure. If I assume this as a reference, atmospheric reference, that means h is equal to P1 by rho g. This is called static head. This is called static head. Now you see, many students have a confusion when they ask that, sir, static head will be the pressure in the fluid when it is at rest. Answer is no. The pressure in the fluid, basically static pressure is the pressure at one section in the pipe, whether the fluid is flowing or not flowing. That is not our concern. Even if the fluid is not flowing, there is a pressure at section 1, that is a static pressure. Even if the fluid is flowing, there will be pressure at section 1, that is also static pressure. So pressure at one section is called static pressure, and when I take it in terms of meter, it becomes static head. Now see, what is happening is this: fluid is flowing with some velocity, let us say v. Fluid has a velocity at this section as v. Now let us say I connect a pipe, L-shaped pipe, something like this. If I connect L-shaped pipe to something like this, so that the face of the pipe opens to the direction of flow. This is the face of the pipe and the fluid is coming in this direction. You know what is going to happen? The fluid is going to enter in this pipe, and what I am going to observe is this: fluid is going to rise in this particular pipe up to some height which is more than this particular h. That means what I observed, that if I put this kind of pitot tube, this is called pitot tube, if I put this tube which is L-shaped tube in the flowing fluid, fluid is going to enter and it is going to rise up to some height which is capital H. Now, why this has happened? By the way, I'll discuss with you, this is called stagnation head. This is called stagnation head. Now why this has happened? Let's discuss that. I take for that matter, can you please tell me what is the velocity here of the fluid? Velocity here, this all fluid is at rest now. It has gone to this level, but it is at rest now. There is no velocity of flow. If there is no velocity of flow here, there is no velocity of flow here, there is no velocity of flow even at the entry of the tube. Let us take this section, this point as 2 and this point as 1. Now let us apply Bernoulli equation. Let us apply Bernoulli equation between section 1 and 2. Section 1 is just outside this pitot tube and section 2 is inside pitot tube. Now let me apply the Bernoulli equation. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2, and I am neglecting the fluid friction. I am assuming that there is no friction here. Z1 is equal to Z2 because it is horizontal only. So Z1 is equal to Z2. Moreover, now V2 is 0 because, as I told you, the moment fluid enters the pitot tube, its velocity becomes 0. So V2 is 0. And now let us say what is V1 square by 2g. V1 square by 2g, V1 is actually V. We said velocity here is V of the fluid which is flowing. So V square by 2g is equal to P2 by rho g minus P1 by rho g. P2 by rho g minus P1 by rho g. And you know what is P2 by rho g? I am assuming that pressure here is this, and this height I am neglecting, that is not significant height. So this pressure is P atmosphere. So what is pressure here? Let's say pressure here is P2, same as this pressure, same entire pressure. So P2 is equal to P atmosphere plus rho into G into capital H. So if I take this as a reference, I get capital H is P2 by rho G. That means this is the stagnation head. So I replace it as capital H minus small h, and V2 is equal to 2G capital H minus small h under root. This is the velocity of flow which this pitot tube has measured. You know what has happened is this. What is the difference between point 1 and point 2? At point 1, fluid has pressure also and fluid has kinetic energy also. Potential energy is same at 1 and 2. At 1, fluid has pressure also and kinetic energy also. At state 2, kinetic energy is 0. So that entire kinetic energy gets converted into pressure head. That is what we see, level has increased. So pressure energy plus kinetic energy. Pressure energy plus kinetic energy is equal to only pressure energy. So what is kinetic energy at this point is equal to, what is the pressure energy, what is the total pressure energy here minus pressure energy here, which you can calculate like this. So this particular part is called kinetic head. This is called kinetic head, and this kinetic head is used to calculate velocity of flow. So what we understood now is V is equal to 2G H minus small h. What is capital H? This is the stagnation head. Why the name stagnation head? Because when you make the flowing fluid come to rest, then its entire kinetic energy becomes potential energy. And whenever you make some fluid which is flowing to come at rest, that is called stagnancy. So it is called stagnant because you have made it come to rest. So stagnant head, static head, and this is the velocity of flow. Wherever you will keep the pitot tube, you will get velocity at that. And now this is the theoretical value. If we want to calculate actual value, then the formula will be equal to this. So you will say, sir, actual velocity of flow through pitot tube is equal to coefficient of velocity into 2G stagnation head minus a static head. That is the velocity of flow at any particular point which we want to measure through pitot tube. Now see, this is the question actually he is going to ask you in the pitot tube. And let me tell you one or two more important things here. Pitot tube is used to find out the velocity at particular point. If I take pitot tube above or down, you know one thing, that the maximum velocity of flow in a pipe is at the center, because for laminar flow you get the parabolic profile. That means maximum velocity of flow is at the center. So if I put the pitot tube at the center, I get maximum velocity of flow. As I bring the pitot tube at the top or I make it at the bottom, velocity of flow decreases. So if I want to find out the profile, velocity profile, it is important for me to make the pitot tube move and get velocities at different points, and that way I can make the velocity profile in the pipe flow or any other particular flow. Even in the river flow, I get the profile like this. So pitot tube, if I move top and bottom, velocity of flow will decrease. There is another way in which I can basically make pitot tube change. I can change the direction of pitot tube also. Let's say presently pitot tube is put like this. Velocity is coming this, and pitot tube it enters and give you stagnation head. What if I start rotating pitot tube? What will happen if I start rotating pitot tube? The moment I rotate pitot tube, then the fluid which is entering the pitot tube keeps on decreasing. And once I rotate it by 90 degree from this position, if I rotate by 90 degree from this position, then no fluid enters the pitot tube. And for next 180 degree, no fluid enters the pitot tube. And from 270 degree to 360 degree, again fluid starts entering the pitot tube. So you know, this is the roughly variation. Let us say theta, presently theta is 0 degree. I assume this is the theta 0 degree. Presently what is the head shown by pitot tube is stagnation head. The moment I come to 90 degree, its head becomes small h. That means these two become equal. Why? Because no fluid is entering here. So stagnation head becomes equal to static head. And next 180 degree, that means up to 270 degree, it remains small h. Then from 270 through 360 degree, it again becomes capital H. So somebody asks you how the stagnation head changes when I rotate pitot tube. Answer is, when I rotate pitot tube, then the stagnation head becomes static head, and for particular angle angle, that means 0 to 90 degree stagnation had decreases, and to 90 degree to 270 degree, that means for 180 degree it remains small h only, and then it again start increasing. So the variation of pitot tube will be when you raise it, when you lower it, or when you change the angle. This is the variation which is possible in the pitot tube. That is what we can understand. This is the two variations he is going to ask you in the pitot tube. So one is used to find out the velocity profile, another is used to basically understand the variation of the angle. Now this is pitot tube. Actually you do not put always manometer, you do not always put piezometer and pitot tube differently. You use pitot tube in these two versions. Let me give you these two versions. They are very simple versions how pitot tube is used. Let me give you this version. This is one version. What happens is, one end of pitot tube is made piezometer and another end is made pitot tube itself, and I put some kind of fluid whose density is lesser than the density of the fluid which is flowing. So let us say this is the density of the fluid which is flowing, this is the density of the fluid, rho s is less than rho. It becomes inverted U tube manometer, differential manometer but inverted U tube. And let us say limb difference here is y, limb difference is y. Pressure here is more, stagnation pressure, pressure here is less, static pressure, and this end of pitot tube is almost put below this end because I don't want there is a losses are with the length, so I don't want that. So this is the piezometer, this is the pitot tube, and this is single tube only. Now what is the velocity? Let's say this is y. So we know that v is equal to root of 2g capital H minus small h. This is what we have known. This is how it is done. Or we know that v2 square by v square by 2g is equal to we know this this is the capital H minus small h. That means P2 by rho g minus P1 by rho g, or P2 minus P1 by rho g. This is what we have seen. This is how it is to be calculated. P2 by rho g, v square by 2g. This is what the Bernoulli equation we know. Now this is the difference of pressure head. I will use the concept of manometer. Now this has become manometer, inverted U tube manometer. I use the concept of manometer to calculate this now. Let's see how it can be used. This pressure is P2 here, this pressure is P1. So P2 minus P1 by rho g is equal to 1 minus rho s by rho into y. Now for this you need to go and understand the concept of manometer, which already I discussed with you. If you know this concept of manometer, you can calculate it. So P2 minus P1 by rho g will be equal to this. Now if I put this term here, that means it is equal to 1 minus rho s by rho into y. V2 square is equal to 2g into h, 2g into capital H minus small h. This is the velocity we were calculating. And how do we calculate h minus small h? H minus small h is 1 minus rho s by rho into y. So if you know the value of rho s, we know the value of rho, we can directly calculate what is the value of h minus h using this as a inverted U tube manometer. Now suppose I want to use U tube manometer, not inverted U tube but U tube manometer. How shall I put the pitot tube? You see what is the kind of arrangement I can get for that. Can you tell me what is this manometer now? U tube or inverted U tube? This is mercury. This is the fluid which is flowing of density rho. This is the density of mercury. This is the limb difference because P2 is more than P1. Again, what is the formula now? V square by 2g. Yeah, V is equal to root of 2g capital H minus small h. And how do we get capital H minus small h? Is equal to now, okay, rho mercury minus by rho minus 1 into y. All we need to do, we need to insert this particular value in this formula, and we are going to get what is the velocity of flow at this particular point. As I told you, for this to know, you need to go and understand the concept of manometer. Just now also I did with you. This actually is nothing but P2 minus P1 by rho g. This is how we have to calculate. So pitot tube can be used with inverted U tube manometer. It can be used with U tube manometer. Only two type of questions come from pitot tube. One is direct stagnation head and static head he will give you. So kinetic head is the difference of stagnation head and static head. Another question will be when he is using it as U tube or inverted U tube manometer. In that case you need to either use this formula U tube manometer like this, or you use to this formula which is used for inverted U tube manometer. When shall we use U tube manometer? When the pressure difference is more or the velocity of flow through pipe is more. When shall we use the inverted U tube manometer? When the pressure difference is small or velocity of flow is small, then we use inverted U tube manometer. And this U tube and inverted U tube manometers are used to calculate velocity of flow at particular point. Now suppose he asks you to calculate discharge through pitot tube. How shall you calculate discharge through pitot tube? You will say, sir, we need to calculate average velocity for that. How shall you calculate average velocity for that matter? You say, sir, I should know the profile of velocity. I should know profile of velocity. I will discuss with you somewhere else that when the laminar flow through pipe is considered, then average velocity of flow is equal to maximum velocity of flow by 2, and discharge is average velocity of flow into area of cross section of the pipe. Now if I put the pitot tube at the center, then what I get is maximum velocity, and I know average velocity is maximum velocity by 2 for laminar through pipe. So I can calculate discharge using this formula. So you will say, sir, you can calculate discharge through pitot tube if you know velocity profile, because in that case we know how average velocity is going to change with maximum velocity, and that relation I can use to calculate the discharge through pitot tube. But for that profile should be known. I am going to discuss that profile in viscous flow with you, then you will understand that. And pitot tube can be used to measure the velocity of flow through a river also. If you do that, the only difference is if I put piezometer in the river, if I put any piezometer in the river, then it is not going to show any head. That means pressure, there is no river flow is not a pressurized flow, so there is no static pressure, as you know that. River flow there is no static pressure. The pressure here everywhere is the atmospheric pressure, and I am neglecting the hydrostatic pressure difference. I mean, even if the hydrostatic pressure is there, if I put a simple tube in the river, then the level of water outside and inside will be same. That means small h is equal to 0. So whatever value of h I get, that value is nothing but root of 2gh. So whatever h I am getting, that gives me direct velocity. So for river flow or open channel flow, the only difference in the formula of pitot tube is small h which I was getting through piezometer will be 0, and whatever value I get here, that value directly gives me the this particular velocity at that particular point. And though I will discuss profile of velocity somewhere else, but I tell you in case of rivers, the profile will be something like this. Maximum velocity of flow is at some depth from the free surface. V maximum is at some depth from the free surface, and at the free surface velocity is not maximum, but at some depth from that. That particular profile can also be made using pitot tube. Now just go for all these concepts. So what we have done so far, before I go for questions, in fluid dynamics I started with what is the dynamics, second law of Newton, dynamics, kinematics, what are the forces important, and then I discussed with you Euler equation, assumptions, Bernoulli equation, which format we should write Bernoulli equation for real fluid, and how to use Bernoulli equation in different applications, and then the three devices on the basis of Bernoulli equation: orifice meter, venturimeter, pitot tube. Believe me, one question certainly comes from this particular part, so revise these concepts good. I will go for some questions. Okay, so let's go for some numericals now on the basis of whatever we have done. So let me read some questions here. This was a question asked in 1987 GATE exam. A mercury manometer is given, is attached to a section of pipe as shown in the diagram. Mercury levels are indicated when there is no water flowing through the pipe. When the water starts flowing through pipe continuously at constant rate in the direction of arrow, the level of mercury at B will. So what is going to happen? So let me make some sense from this particular question. He says that mercury manometer is attached to a section of pipe. Actually he is saying it a pipe, but this is the Venturimeter attached to pipe. So there is a converging section, there is a throat, and then there is a diverging section. One limb of the manometer is attached to the pipe, and another limb B is attached to a throat of Venturimeter. So in the beginning there is no water flowing. So when there is no water flowing, what is there? Atmospheric pressure everywhere. Let us say that, or equal pressure everywhere. So pressure at these two levels are same, and this is what is the diagram shown. That means both the limbs are showing same level. So there is no limb difference in the mercury as the fluid starts flowing. But you know, when fluid starts flowing, that means when the liquid starts flowing, then he is asking us the question, what will happen to the level of B? Will go down, will go up, or will remain same? That is the question. Now this is very simple question of Venturimeter. You must have answered this already. You must be knowing this. It's very simple question. When the fluid starts flowing, you need to think of continuity equation and Bernoulli equation. Now, let us say this side. If I take this as section 1, this as section 2, area at section 1 is less than area at section 2. And because of continuity equation, V1 A1 is equal to V2 A2. So if A1 is less, V1 is more than V2. So velocity of flow at section 1 will be more than velocity of flow at section 2. And since Z1 is equal to Z2, so both the sides datum is same. Now if we put the thing in Bernoulli equation, so wherever there is a velocity is more, pressure is going to be less. That means P2 is more than P1. And if P2 is more than P1, don't you think there will be more pressure on this side? That means then the mercury is going to go down this side and mercury is going to rise in this direction. And hence the mercury limb difference can be seen something like this. Now there will be some limb difference in the mercury, let us say Y. So when pressure at P2 is more than pressure at P1, so this side mercury is going to go down and this side mercury is going to go up, and there is going to be a limb difference. That limb difference is going to show the pressure difference. So there will be pressure difference 2 minus 1, and that is the liquid level in limb B is going to rise. That is our answer for that. Now let me ask you a question. Why he has given you direction of flow? Suppose he gives you direction of flow this side. Suppose this is the direction of flow. How your answer is going to change? Answer my question. If direction of flow given is different, how your answer is going to change in this particular case? Answer is not going to change. Again the liquid level is going to rise, because direction of flow is related to something which is friction loss. We are not considering that. Friction loss we are not considering. We are considering the pressure difference because of area change. Area here is more, whether fluid is flowing from this side or to that side. Area at section 2 is more, pressure at section 2 is more. So limb is only going to, mercury is only going to rise in B, whether direction of flow from this side or direction of flow is from that side. So remember this particular thing. Now let me go for next question. Next question, let me read out. This question is for the pitot tube, inverted U-tube pitot tube. Water flows through a pipe of diameter 0.3 meter. What would be velocity V for the conditions shown in the diagram? So there is section 1 where there is a velocity of flow V. Section 2 is inside the pitot tube and it is inverted U-tube manometer. So pitot tube and piezometer are connected to make inverted U-tube manometer. And the liquid in the inverted U-tube manometer has specific gravity 0.8 and the limb difference of that is 0.3 meter. Now what we have to answer is that what is the velocity of flow V? Now we have already discussed in the video, I have discussed with you inverted U-tube manometer. Kinetic head V square by 2G is equal to difference of stagnation head minus static head. As you can see here it is more pressure, so I can see this particular thing is the stagnation head, this particular thing is the static head. So V square by 2G is equal to H minus small h. Capital H is the stagnation head, small h is the static head, and V square by 2G is the kinetic head for that. Now capital H minus small h given to us is 0.3. But you know this cannot be directly written as 0.3 because this is given in terms of another fluid which is of specific gravity 0.8. So how we have to solve that is V square by 2G is equal to 1 minus specific gravity of this fluid over specific gravity of the water into Y. Y is the difference of the limb in the two, and that is 0.3. So that is how we have to analyze it, calculate it, and if we put all the values we are going to get this value of velocity or kinetic head. Now in the pitot tube, concept is very simple. Kinetic head is difference of stagnation head and static head. Many students face trouble in memorizing this formula, from where this formula has come. Let me give you the concept for that, from where this formula comes in terms of your U-tube and inverted U-tube manometer. Let us say I have U-tube manometer here, though that particular manometer as a topic will be covered in different domain. I will cover that separately. But let us say there is a U-tube manometer and let us say this is pressure P1, this side is pressure P2, and this fluid which is flowing in the pipe is of density rho, and this fluid is mercury of density rho Hg or specific gravity Shg. Let us say specific gravity of this fluid is S. Now the limb difference between the two is mercury limb difference is, let us say, Y. Now let us say how to find out the pressure P1 minus P2. What we do is we take the pressure at the same streamline. Remember that if you are taking pressure P1 at this point, you take pressure at section 2 also on the same streamline. That is also you have to do. And now let us say this height, this particular height is X. Let us say this height is X. Now when we draw the reference in the two limbs, then what we understand is that at point A and at point B, pressure is going to be same. PA is equal to PB. Why? Because same fluid, same level, so pressure is going to be same. So P at A is equal to P at B. Same fluid, same level. What is PA? If I calculate what is PA, then PA is equal to P at this point, P1 plus rho of the fluid into G into X plus Y. So hydrostatic law, P1 plus rho G into this entire height. Rho is the fluid which is flowing into G into X plus Y. What is PB? PB is P2, this P2 plus rho into G into X plus rho mercury into G into Y. This one is mercury, this one is of density rho. So rho into G into X plus rho mercury into G into Y. If I equate these two, what I am going to get is this. P1 minus P2, rho Gx will get cancelled out. Rho mercury minus rho into G into Y. That is the answer which I am getting. But suppose I want to find the answer in terms of difference of pressure head. Then I am going to write P1 minus P2 by rho G is equal to rho mercury by rho minus 1 into Y. And what is this P1 minus P2 by rho G? This is difference of pressure head. That means what is the pressure here minus what is the pressure here. That is called difference of pressure head. And it is calculated in terms of now density or specific gravity of heavier fluid minus the specific gravity of the fluid which is flowing into Y. That means Y is the difference of the limb of this mercury in the two limbs. What is the difference? That is the value of this. Now suppose the pressure difference between the 1 and 2 states is very less. Pressure difference is not much or pressure difference is not much. Then instead of going for U2 manometer, we go for inverted U2 manometer. Let me clean it up again and make inverted U2 here. Let us say I have inverted U2 manometer between the two sections. Okay, this becomes inverted U2 manometer. Now the fluid which is used in inverted U2, let us say this limb difference is Z. Reference line will be this. Let us say density and specific gravity of the fluid which is in inverted U2 is rho S and SS. The density and specific gravity of the fluid which is flowing is rho and S. The difference of the limb difference of this fluid in the two sides is Z. Then you know what? P1 minus P2 by rho G. This rho G will be of the fluid which is flowing. And I will say this is the difference of pressure head. That is equal to now 1 minus rho S by rho into Z. Now rho S obviously is less than rho because this cannot be negative. Rho S is less than rho. In this case, how we have calculated? We calculated P1 minus P2 by rho G is equal to rho mercury by rho minus 1 into Y. This is U2 manometer, this is inverted U2 manometer. So difference of pressure head, this one and this one is called difference of pressure head. Difference of pressure head between two sections that can be calculated either through U2 or through inverted U2 manometer. You are using U2 manometer if the difference of pressure head is more. I give you hypothetical example, hypothetical fluids flowing in this. Let us say the fluid which is flowing in the pipe is water. That means for water the density is 1000 kg per meter cube. Let us say the inverted U2 manometer which I am using, it has fluid density of 800 kg per meter cube. That means its specific gravity is 0.8 and mercury density we know 13,600 kg per meter cube or specific gravity is 13.6. Now when I want to calculate these two, can you tell me what is the value of then 1 minus 800 over 1000 into Z? that is 1 minus 0.8 or 0.2 Z. This is the value which is coming. And what about this 13,600 over 1000 minus 1 into Y? So that comes out to be roughly 13.6 minus 1 into Y, 12.6 into Y. Now let me compare the two. For U-tube manometer and for inverted U-tube manometer, these are the values I am getting. P1 minus P2 by rho G is coming out to be 0.2 Z and 12.6 into Y. Now you understand one thing, that if this value is very less, this value Z will be more. If this value is more, this value is very small. So if P1 minus P2 is very high, if P1 minus P2 is very high, then I should go for it so that value should not be very high. If this value is high and 0.2 I am taking, then Z is going to be very high. That is not good. So I use the U-tube manometer when the difference of pressure is high. I use the inverted U-tube manometer when the difference of pressure is less. Because if the difference in pressure is less and if I use this, then Y will be very small. I cannot even measure it. Difference of pressure is less, then I go for it and Z will be significant. I can measure it. So suppose he asks you, why do you use U-tube manometer or inverted U-tube manometer? Answer is U-tube is used when difference of pressure head is more, and I use heavier fluid than the fluid which is flowing, something like mercury. And I use inverted U-tube manometer if difference of pressure head is small, and I use a fluid of lesser specific gravity than the fluid which is flowing. That is how it is to be done. And then we have already discussed in the analysis of the pitot tube, that pitot tube analysis can be done. This is the typical pitot tube. I attach the piezometer and attach the pitot tube. Now this is the piezometer. Whatever pressure is here, this piezometer is going to give me the value of static head here. Whatever is the velocity here, that becomes 0, and I am going to get the stagnation head here, capital H here. And pitot tube may you get V square by 2G is H minus small h, or V is equal to 2G capital H minus small h and rho. But in this case, the fluid which is in the piezometer or pitot tube is same as the fluid which is flowing. But suppose I attach this piezometer and pitot tube in the form of now inverted U-tube manometer, as the question was, then what is going to happen is I am going to get this particular situation where there will be inverted U-tube fluid of specific gravity or density rho s, and again I am going to get H minus small h, V square by 2G. But now this H minus small h will be calculated in the form of 1 minus rho s over rho into Y, where Y is the difference which is basically this difference, again this is H minus small h. This is how we are going to use the pitot tube for inverted U-tube and U-tube manometer. Please note it down. Okay, so let me take two more questions here. This question is really interesting question and good question, and it explains the philosophy of the exhaust fan also. Question is, a fan in the duct is shown below, which sucks air from ambient and expels it as a jet at 1 meter per second to the ambient. So there is a duct which is shown. This is duct, and it is taking air from the ambience only. This side is the ambient condition. Ambient means pressure will be atmospheric pressure, and it releases the jet of air to the ambient only. That means this jet of the air which exhaust fan is releasing, that is also being released to the ambience. So suction is done from ambience and jet is also expelled to the ambience. The velocity of jet is also given as 1 meter per second. So the velocity of flow of this jet is 1 meter per second from here. Determine the gauge pressure at point marked as A. So you have to tell what is the pressure at this point A. Density of the air is to be taken as 1 kilogram per meter cube. Now philosophically, you need to understand what this exhaust fan does. Exhaust fan is doing the suction actually. Its blades are so designed that it's upstream. This is the downstream of the fan. This is the upstream of the fan. So the blades of the exhaust fan are so designed that on the upstream side, the pressure is lesser than ambient pressure, and because of that only the suction takes place. If I ask you a question, why the air is flowing this side, what is the reason of the air to flow this side, you will say, sir, pressure here is more, pressure here is less. And what is creating lesser pressure than ambience? You will say, sir, lesser pressure is being created by the fan because of its blade design. That means if the pressure here is atmospheric pressure and the fluid is flowing this side, that means certainly pressure here is the vacuum pressure. Now vacuum is nothing but negative pressure, negative gauge pressure is called vacuum pressure, and that negative pressure is created by the fan. Now how shall we know what is the pressure at this point? For that we need to apply Bernoulli Equation between two sections at which we know the conditions. Now see, at state 1, if you ask me, if I take this as section 1 and if I take this as section, let us say A, which is given to me, section A, I want to calculate pressure at section A. I am given the velocity at section A. Do not misunderstand velocity at section 1. Section 1, if I am considering atmospheric pressure, then this is also infinite area section. So you cannot say the velocity of the jet at section 1 is 1 meter per second. If the velocity of jet is given in this duct as 1 meter per second, throughout the duct the velocity is going to be same because of the continuity equation. Why? Because the area of cross section of the duct is given to be same and density of the air is also given to be constant. So if I use the continuity equation, then velocity of the jet at this side will be equal to velocity of the jet at point A also. Velocity of jet cannot be taken 1 meter per second at the exit where you are taking atmospheric pressure. Because if you take atmospheric pressure, then it is open to ambience, and if it is open to ambience, velocity cannot be taken there because it is a large cross-sectional area. So the most important point here was that velocity of the air which is flowing at point A is 1 meter per second. Throughout the duct, velocity of flow is 1 meter per second. Now I know velocity here. There is no velocity here. I know I want to calculate pressure here. I know pressure at this particular point. I know Z at this point is equal to Z at this point. Now if I put all these values, let us see, do I get the pressure at section A? Let us see what is the pressure at section A. So I use the Bernoulli equation. I use Bernoulli equation at section A and section 1. Let us say P at A by rho G plus VA square by 2G plus ZA is equal to P1 by rho G plus V1 square by 2G plus Z1. Now ZA and Z1 are equal and velocity at section 1 is 0. This pressure at 1 is nothing but P atmospheric, and I want to find out what is the pressure at point A. Now if I consider the pressure at atmospheric pressure to be 0, if I take let's say atmospheric reference, you know gauge pressure and vacuum pressure are measured with respect to atmospheric reference. That means I am standing at atmospheric reference. If the pressure is more than atmospheric, it is gauge pressure, positive. If the pressure is less than atmospheric, it is vacuum pressure or negative gauge. So I take atmospheric pressure also to be 0. So what is PA by rho G is equal to minus VA square by 2G. G gets cancelled out and what I get is PA is equal to minus VA square by 2 into rho. Now what is given to me is V is 1, density is 1 over 2. I get minus 0.5 Pascal. That is the value of pressure at point A. That is a vacuum pressure, and exhaust fan creates the vacuum only. So gauge pressure actually for me is nothing but minus 0.5 Pascal, which I have calculated. Now let me tell you the direction of this particular entire thing. What is we are getting? Let us say this is the P is 0 Pascal reference. This is called absolute reference. This is called absolute reference for me, where pressure is 0 Pascal. This one is called atmospheric reference, where pressure is atmospheric pressure 10⁵ Pascal. Atmospheric reference. Now whenever the pressure is more than atmospheric pressure, it is called gauge pressure, and this is the positive side. Whenever pressure is less than atmospheric pressure, it is called vacuum and it is called negative pressure. Now in this situation, the pressure at A was negative pressure. Atmospheric pressure is this and this is the negative pressure, and hence I am getting 0.5 Pascal, which is negative. That means I am seeing it with respect to atmospheric reference. If you make atmospheric reference as a reference, if you select, you take the pressure at atmospheric pressure as 0 and you get the negative pressure. So in this case, I am getting suction pressure, which is the negative gauge pressure or the vacuum pressure 0.5 Pascal. Had the question asked you what is the pressure at A in absolute reference, then we would not have neglected P atmosphere. Then we would have taken P atmosphere as
10 raised to power 5 Pascal, and then minus 0.5, 10 to 5 minus 0.5 is the absolute pressure. Had the question asked what is the vacuum pressure, we would not have used negative sign, we would have said 0.5 Pascal vacuum is the pressure at this particular point A. This was a question, I hope you understood the concept. That is actually the philosophy of the duct or vacuum creator. Let me go for this question, that is Venturimeter of 20 mm throat dia is used to measure velocity of water in horizontal pipe of 40 mm. If pressure difference between pipe and throat is given to be 30 kPa, what is the velocity of flow? Now this is nothing but a simple question of Venturimeter, not a difficult question. Let me answer this question. He has already given you, now there is no need to go for manometer, but let me make the diagram here for manometer again. This is the diagram given to me. He is giving you diameter of the pipe as D1, diameter of the throat as D2. So he says there is a throat diameter of 20 mm and pipe is Venturimeter of 20 mm, pipe diameter is given as 40 mm. This is given to us, and pressure difference is given 30 kPa. So let us say this is section 1, this is section 2. So P1 minus P2 directly is given 30 kPa to us, and we have to find out what is the velocity. What is the velocity, flow velocity? That is what we have to find. Velocity of flow through this section. I think V1 is something which is to be calculated. Now let us say first we go for continuity equation. V1 A1 is equal to V2 A2. That is a continuity equation. And you know A1 A2 are cross section area at pipe and throat, and V1 V2 are the velocities. So he is asking you to calculate the velocity of flow in the pipe, that is V1. Now area can be written as a square of diameter, so V2 into D2 square. That is how it can be calculated. Now let us say how do we express V2 in terms of V1. V2 is V1 D1 by D2 whole square. Now what is D1 is 40, D2 is 20, so that means it is 2, that means 4 V1. V2 is equal to 4 times V1. What is V2? Velocity of flow in the throat. That is what we have calculated. Now let's go for Bernoulli equation. If I apply the Bernoulli equation between the two sections now, manometer actually is used to calculate the pressure difference, which he has already given us. So we do not require the manometer. Just forget about this manometric concept. Now apply the Bernoulli equation between section 1 and section 2. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Friction is not to be considered, so I am using Bernoulli equation for this. Z1 is equal to Z2 for me. Now P1 minus P2 is given as 30 kPa. I cancel g throughout. I get P1 minus P2 by is equal to 30 kPa. Now let's put it this way. P1 minus P2 by rho is equal to V2 square minus V1 square by 2. Now what is V2? 4 times V1. So that whole square will become 16 V1 square minus V1 square by 2. That means 15 by 2 V1 square is equal to 30 kPa into 1000 divided by 1000. Density of the water is taken as 1000, and this is also 10 raised to power 3. It gets cancelled out, and from here I get V1 is equal to 4 under root, that is 2 meter per second. So velocity of flow in this I calculate 2 meter per second. So I believe this question was very simple question. It was pressure difference was also given. You are not supposed to calculate pressure difference also. So only diameters are given. You have to use Bernoulli equation, and you have to take two sections, one in the pipe, another is in the throat. So pipe mein velocity of flow is to be calculated, not in the throat. Throat is a venturimeter. So that was the question given to us. If pressure difference is not given, we are given limb difference of the mercury, then pressure difference can be very easily calculated as, let us say P1 minus P2 by rho g is equal to rho mercury by rho of the flowing fluid minus 1 into limb difference, that is y. This is how we have to calculate the difference of two. So just note it down.
So let us go for this question now, which is again related to your this manometer. This is U2 manometer. Arrangement is shown here, which measures the velocity of gas which is flowing. So there is a gas which is flowing through this pipe, and the density of the gas is given as 1 kilogram per meter cube. it is flowing through the pipe. The manometric fluid is water. So normally we know that in the manometer we are using fluid which is mercury, but in this case the fluid which we are using in the manometer, it is water. So we have to take the density of the water. Density of the gas is given 1 kilogram per meter cube, and we know density of the water is 1000 kilogram per meter cube. Though it was given in the numerical, the density of the water is 1000 kilogram per meter cube. Now velocity of flow is given as 20 meter per second, and the differential head in millimeter. Now what is the limb difference, that we have to find out. What is the limb difference? This is nothing but a pitot tube, and this side pressure is more because it is the stagnation head, and this side pressure is less because this is the static head. So if you see carefully, then this particular is capital H is the stagnation head, because that includes the kinetic energy also and pressure energy also. This side is a static head which is small h, and that is only pressure energy. So pressure energy at this point plus kinetic energy at this point gives you stagnation head. And now we have to find out what is the velocity of flow. We know from the pitot tube, that is we have discussed pitot tube questions just now. This question is similar to the pitot tube questions. Let me give you the pitot tube questions to you. In the pitot tube we have discussed that whenever we join the pitot tube using some particular fluid. Now you see this question we have just now done. This is the inverted U-tube manometer for pitot tube. Inverted U-tube manometer. And if we are given the difference of the limb, let us say y, velocity is v, we have just seen v square by 2g is equal to rho of the fluid which is flowing, this is rho s. So 1 minus rho s by rho into y. This is just we have done, that is the inverted U-tube manometer. But this is the U-tube manometer, this is the differential U-tube manometer, in which water, that is a heavier fluid than gas, is used. So what we have to do is v square by 2g is rho of water over rho of air minus 1 into y. Now v is given to us as 20 meter per second, rho w is 1000 and rho of air is 1, very less. So minus 1 into y. Now y is the limb difference which we want to find out. This is the limb difference y or h we want to find out. So if we solve this question, we are going to get some value of y, and in millimeter, because he has asked you to calculate that in millimeter, this is what the value of that limb difference in millimeter is going to be. So this is a very important question. Of late the question is coming from this part of pitot tube repeatedly. U-tube manometer, inverted U-tube manometer, same concept which I discussed, just memorize that particular concept. Now next question is also very simple question. This is a Venturimeter question. Water flows through Venturimeter जिसका internal diameter of the pipe is 80 millimeter and diameter of the throat is 40 millimeter. So we know that D1 is 80 millimeter and D2 is given as 40 millimeter. So if we say V1 A1 is equal to V2 A2, V1 D1 square is equal to V2 D2 square, and from there we get, if we want to find out velocity at section 1, V1 is equal to D2 over, or V2 if I put, V2 is equal to V1 D1 divided by D2 whole square. Now this is nothing but V1 80 over 40 whole square, that is nothing but 4V1. So V2 is coming out to be 4V1. And now P1 and P2 are also given to us, pressures are also given to us. Assuming this venturi to be horizontal, neglecting friction, we want to find out the internal velocity in meter per second. So it is a very simple question. Same question was asked previously also. Let's go for Bernoulli equation. P1 by rho g plus V1 square by 2g is plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Now Z1 Z2 gets balanced out, and we are given P1 as 400 Kelvin kilopascal and P2 130 kilopascal. So let me put all the values here. I put P1 minus P2 by rho g is equal to V2 square minus V1 square by 2g. G gets cancelled out, and V2 can be written as 4V1 square minus V1 square. V2 is 4V1, so that will be 16V1 square over 2. Eventually P1 minus P2 by rho comes out to be 15V1 square by 2. Now let me put the values here. This is 400 minus 130 kilopascal means 10 raised to power 3. For water it is 10 raised to power 3, 15V square by 2. Now let's see what gets cancelled out. This is equal to now 270. 270 is equal to 15 V1 square by 2. It comes out to be 540 by 15 V1 square. Now this further comes out to be 36 if I'm not wrong. 5 3 is a 45, 45, 5 9, 5 16. Okay, so V1 coming out to be 6 meter per second. If you see, just now I did a question which was exactly same question of this type. So similar question was asked in this particular domain. This is what related to the velocity of flow. Just write it down. Okay, so let's read this long question. It was asked in 2003, but the question is very simple, not difficult. Let me read the question first. Air flows through a venturi and through venturi into atmosphere. Air density is rho and atmospheric pressure is Pa. Throat diameter given is dt and exit diameter is d and exit velocity is u. Throat is connected to a cylinder containing frictionless piston which is attached to a spring. The spring constant is K. The bottom surface of piston is exposed to atmosphere. Due to flow, the piston moves by x distance, and assuming incompressible frictionless flow, find the value of x. Now that is the question given to us. Now let's try to make some sense. This diagram is also given to us, and these are the four answer choices what we are given to calculate the value of x. So let me make some sense of the question. This is the venturimeter which is given, and the diameter at the throat is dt, the diameter of the exit is d, and the velocity of flow given is u. That exit velocity is u, exit diameter is d, and then there is a mechanism where is a piston mechanism is there. Piston stiffness constant is K. You know why this stiffness constant of piston is used to calculate piston force, and because the pressure at the throat is less, pressure here is P atmosphere, pressure at this side is also P atmosphere. So piston is subjected to some pressure force, and that is atmospheric pressure, the pressure at the throat. That difference of the pressure applies force on the piston, and the piston moves by small distance, let us say x. The diameter of the piston given is ds. That is what we have to put the things together to calculate the basically value of x. So air flows through venturi into atmosphere, density of air is given, atmospheric pressure is given Pa, and that means the pressure at this point is Pa, and the pressure at this side of the piston is also Pa. So understand one thing, on one side of the piston which is open to atmosphere, pressure is Pa, and on the other side of the piston, pressure is the pressure which is at throat. Let's call it section 1. So pressure on this side of the piston is P1. So what is the net force acting on the piston? Force acting on piston is nothing but Pa minus P1 into pi ds square by 4. What is pi ds square by 4? That is the piston area of cross section, and this is the pressure difference acting on the piston. So Pa minus P1 into pi d square by 4 is the force acting on the piston, but that force is also K into x. So if in somehow we are in position to calculate the Pa minus P1, we will be in position to calculate the value of x also. Now how to calculate Pa minus P1? That can be calculated if we apply the Bernoulli and continuity equation between section 1 and section 2 or exit section. So let's solve this question. It's a very simple question, not a difficult question here. Let's try to understand this. I apply first continuity equation between section 1 and exit. Let us say this is exit is section 2, this one is section 1. So when I apply continuity equation between section 1 and 2, I get A1 V1 is equal to A2 V2. Rho 1 is equal to rho 2, because in the question it is given that it is incompressible. That means density at both the section is equal, and we also know that it is equal to d1 square d2 square V2. That means if I want to find out velocity at section 1, that will be equal to d2 by d1 whole square into V2. What is a d2? That is capital D. What is a d1? That is a dt whole square into what is V2, that is capital U. So V1, that is velocity through throat, velocity at the throat is equal to this particular value into capital U. Now let's keep this particular value V1 as d by dt whole square into capital U. Keep this thing in mind now, and let's apply the Bernoulli equation. Let's apply Bernoulli equation between section 1 and section 2. P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Since Venturimeter given is horizontal, Z1 is equal to Z2. And now what is P1 is the pressure at throat, and what is P2? It is the atmospheric pressure which is at section 2. Now we have already obtained V2 is nothing but capital U, and V1 we have obtained this. So let me find it. P1 by rho g plus d over dt whole square into U square whole square. V1 square means this value will be raised to power 4 over 2g is equal to P2 by rho g plus U square by 2g. Now see this equation, Bernoulli equation, carefully. What we need to find out is PA minus P1. Now P2 is nothing but PA. So let's find out PA minus P1 by rho g is equal to d over dt raised to power 4 U square by 2g. U square by 2g is on this side also, so that is minus U square by 2g. That is the value we are getting. Now you understand, I can take certain things common from here. Let us say I take U square by 2g common, then this particular thing becomes g gets cancelled out. So what I get from here is PA minus P1 by rho is equal to U square by 2 into d raised to power 4 over dt raised to power 4 minus 1. I believe that is right. So PA minus P1 by rho is this. So if I want to calculate PA minus P1, it is rho U square by 2, and all we do now here is just substitute this value into this expression. Once I do that particular thing, what I get here is Kx is equal to PA minus P1 is rho U square by 2 d over dt raised to power 4 minus 1. That is the value of it into pi ds square by 4. We want to find out value of x, that is equal to rho U square over 2k. Okay, and 2k multiplied by 4 becomes 8k. I remove this into this. So I believe this is the answer what we are getting. So it's a very simple question. It was not a difficult question. Only thing we have to do is we have to apply the Bernoulli equation between two sections, find out what is PA minus P1. That PA minus P1 acts on the piston force, that is in terms of K into displacement of the piston, and that x value can be calculated accordingly. Very simple question. I hope you understood this. Just note it down. So let's go for this question now. Prandtl tube, and remember that Prandtl tube is also called pitot tube also. So pitot tube, another name for that is Prandtl tube also. With C1, C is basically coefficient of velocity, pitot tube. That means we are not to take any C value is 1. Is used to measure velocity of water. Differential manometer reading given is 10 millimeter of the liquid column with relative density 10. So as we know, the flowing fluid is water, and the manometer fluid is having specific gravity 10. That means it is 10 times denser than water. If we assume G is equal to 9.8, velocity of water will be what? Now let me tell you what is this question given. This question is actually the question of pitot tube only, in which we have got this particular situation. This is the situation which is given to us. There is a pitot tube and having inverted U tube manometer. This is the water which is flowing with density rho W, and there is a fluid which is of specific gravity 10. So that means rho of this fluid is 10 times the rho of water. That means specific gravity of this is let's call it manometric fluid. Specific gravity of that is 10. Specific gravity of water, as you know, is 1, and the difference of the limb is given as 10 millimeter to us. This is given as 10 millimeter. What we have to find is what is the velocity of flow. We have already done many questions of this type. The formula for that now is v square by 2g. That means the velocity kinetic head what we want to find out is equal to rho of manometric fluid over rho of the fluid which is flowing minus 1 into y, the limb difference. Now what is the rho of manometric fluid? That is 10 times the rho of water. So rho m over rho w is 10 minus 1 into what is y, 10 millimeter. I write that in meter. So 10 divided by 1000. that is what is the value of V square by 2g. So what is V coming out to? V square by 2g is coming out to be 9 into 90 by 1000. So if I am not wrong, that is 0.09. So 9 divided by 100 that is 0.09, and from there we can calculate 2g into 0.09 under root, that is the value of velocity. So let me see what is that velocity coming out to be in this particular case. That velocity, if you put in values, that is 1.328, 1.33 meter per second should be the velocity of the flow. So very simple question. I mean, all domains the same question is being asked. Pitot tube and U tube and differential U tube manometer, the same concept is being repeated. So remember this particular question. It's a very simple question. Okay, now let's go for the next question which is given to us. In this question, U-tube manometer is there with small quantity of mercury which is used to calculate the static pressure difference between A and B in the conical section. So we are given a conical section, and in the U-tube manometer, limb difference of mercury, there is very small mercury, and the difference, the height of that mercury is 150 millimeter. So U-tube manometer with a small quantity of mercury is used to measure pressure difference. At a particular flow rate, mercury column appears as shown in this particular diagram. Now you see, because pressure at A is more than pressure at B, so fluid flows actually on the right side. So that means pressure at A is more than pressure at B. What we have to find out is what is the pressure difference, that is number one, and what is the direction of flow. These two things we have to find out. Now let's see how we want to find out is PA minus PB, that is the pressure difference. And if you go through the differential manometers carefully, then that differential manometer will tell you that difference in the pressure between two is equal to the manometric fluid limb difference between the two limbs, but there is the entire mercury in the one limb only. So whatever is the pressure corresponding to this height of mercury, fluid is not given to us, so we take only mercury. Whatever is the pressure difference corresponding to this height of mercury, that is the difference in the pressure. So we say that is equal to rho mercury into G into H. What is rho mercury is given 13,600. This is 9.81 and 150 over 1000. If we put that is PA minus PB. That is a value for us which we have to calculate. And if we put all values here, let me check what value we are getting corresponding to this particular thing. If we put all values here, we are going to get PA minus PB equal to 20 kilopascal. That comes out to be 20 kilopascal approximately. Now let's see answer choices. Flow direction, let's see first. PA minus PB is given as 20 kilopascal. Okay, that is correct. There is no correct answer other than A. Now if you ask me, sir, how to know the flow direction? That is a catch in this question. How to find out the flow direction? My answer is you cannot find flow direction with the data which is given. To find the direction of flow, all you need to do is this. You need to write the entire Bernoulli equation. You need to write entire Bernoulli equation, and for real fluid you need to write the Bernoulli equation. ZA is equal to ZB. So unless until you calculate HF by calculating these conservative energies at section 1 and section 2, you cannot calculate the direction of flow. So suppose this particular values HF is coming positive, then the direction is from A to B. But if this is coming negative, direction of flow is from B to A. Hence you cannot find out the value of, you cannot find the direction of flow unless until the values of and all the conservative energies are calculated. But the kind of question which is given to us in that question, I don't think we can find out the velocities. But if you take the help of answers, then there is only single answer in which PA is minus PB is correctly calculated. Obviously pressure at A is more, that is shown by the mercury. But if we are seeing the answer choices, other three answer choices may PA minus PB correct value is not given. Suppose you are given answer choice PA minus PB is 20 kilopascal. Let us say then you could not have answered whether it is this or this. You could not have answered on the basis of the data which is given. Then you need to write the Bernoulli equation for real fluid, then only you can answer it. Another thing which I want to add here is, suppose he has given you density of this fluid which is flowing also, then in this particular equation you have to write rho mercury minus rho into GH. That is the only difference which will come. Then you could have calculated difference of pressure, something like this. Fine, just note it down.